and welcome to this session on resource recovery. We have 5 presentations this morning, one of them in person and 4 of them are virtual, but I'm sure it will run very smoothly. So we have some time after each presentation for some questions, so please do think of those as the presenters are going through their presentations. After the session, so if you're joining online, please write them in the Q&A and we will pick them up from there. If you're here in person, which many of you are, please raise your hand afterwards and I will come to you if we have time. So without further ado, I'd like to introduce our first speaker. It's Andrew McLeod from Jacobs. So welcome.
Hi everyone. Thanks for making the journey over from the other room. So today I'll be talking about an exploration of hydrogen production pathways in bioresources. And it's a pleasure to be opening this resource recovery session. Just want to give a quick shout out to the wider Jacobs team that have been involved in this work. Most of us are here for today and tomorrow, so and most of us are approachable, so please come and say hello, talk to us. If you're not here and you're attending virtually, then please get in touch. My contact details are on the slides provided. So this is part of a wider thought leadership development that we're having here at Jacobs. So when we got stuck into this, we really thought actually this is quite a complex area. So what was initially going to be a couple of two-page document, a couple of pages, sort of broadened out into these series of discrete thought pieces. And so hopefully I'll be able to touch on these today. So as I mentioned, the hydrogen in the water sector we think is going to be very complex. We think water companies are going to want to understand how they're going to go about producing hydrogen, but also how they might use the hydrogen for their own internal and external needs. And through this thought piece series, we hope to sort of unpick some of that complexity and make that a little bit clearer as to how the sector might engage with the hydrogen economy. So clearly, net zero is one of the primary drivers for why we would be interested in hydrogen. So we've seen this recently at national level with the UK's hydrogen and net zero strategies, where they're looking at an ambition of generating 5 gigawatts of low carbon hydrogen by 2030. Within the sector, at sector level, we've seen hydrogen mentioned many times within the Net Zero 2030 route map, published last year by Water UK. And now we also see the mention of hydrogen in some form within different individual UK water company net zero route maps. With the national level strategy, a lot of that is still out of consultation, so there's still quite a lot of uncertainty around the scale, applications and timings of hydrogen and how that will roll out. So lots to explore and hopefully lots for us to delve into. So there's numerous hydrogen production innovation and commercial projects around the world. In the UK, these are sort of spearheaded, if you like, by several UK water companies. Northern Ireland Water already have a 1 megawatt electrolyser at one of their sites. Recently, an Anglian Water-led project, the Triple Carbon Reduction, was funded through the Ofwat Innovation Competition, partnered by Jacobs and several other water companies as well. And independently, Severn Trent Water and Northumbrian Water and Welsh Water all looking at different pathways for hydrogen production. So what are these pathways and which one is best is the question we'll hopefully address here. So we've identified 5 hydrogen production pathways and we've modelled them here on a model, fictitious, large wastewater treatment works of 1 million population equivalents and co-located sludge treatment centre with about 100 dry tonnes per day. So that's the sort of scale we've decided to model at. Just to introduce the pathways then, so the first pathway is actually the only pathway that sits outside of bioresources, and that is the final effluent pathway. And that involves the electrolysis of final effluent into hydrogen and also oxygen. Next is we go into the bioresources pathways now. So we have the ammonia pathway, which looks at stripping ammonia from sludge liquors, converting that ammonia into hydrogen either by some kind of electrolysis or thermal cracking process. We have the Advanced Thermal Treatment Pathway, or ATT pathway. This involves the production of pure hydrogen from syngas generated by pyrolysis or gasification of raw sludge or of treated biosolids. Next up, we have the steam biogas SBR pathway, and this is the purification of generation of pure hydrogen from syngas generated by reformation of raw biogas. And finally, the steam reformation pathway, steam methane reformation pathway, SMR, which is purification of separation and isolation of pure hydrogen from syngas generated from reformation of biomethane following biogas upgrading. At the end of each of these pathways, we have here these little Lego bricks, and they represent the relative quantities of hydrogen that can be produced by these pathways. So if we examine these pathways, first up is the final effluent pathway. Now, this doesn't sit within Bioresources, but it's useful to look at it here as a benchmark for the other pathways. So this has the potential to generate the biggest quantity of all of the pathways possible. I've shown it here at 3 different scales, 1 megawatt, 10 megawatt, 100 megawatt, and that is the power of the electrolyzer itself. At the moment, outside of the water sector, 10 megawatts is the kind of order of magnitude scale of plants that are going in. Looking forward to 100 megawatts, which is the kind of scale that we expect might be needed if the UK is to achieve its 5 gigawatt higher heat value of clean hydrogen capacity in the future. Individually, each of these components have a high level of readiness, although we have yet to put them together into one single pathway, and that's actually what Anglian Water's triple carbon reduction process looks at. Reasonably flexible, we don't actually have to be co-located to an STC, sludge treatment centre, for this pathway. In and of itself, it has no treatment benefit, but actually it has a great synergy with aerobic treatments through the co-production of oxygen, pure oxygen. So this is actually the crux of the triple carbon reduction pathway, triple carbon reduction project that Anglian Water is leading and Jacobs are involved with, along with Oxymem, who produce a MABR, membrane aerobic biofilm reactor, and this can really maximize the efficiency of that recovered oxygen to reduce the process, the energy involved in secondary treatment, and also potentially a step change in process emissions related to nitrous oxide from treatment. So we get a big co-treatment and a big carbon benefit over and above the actual production of hydrogen. So that's an interaction with the wastewater side of it. What about the bioresources side of it? Well, the first thing to say is that the bioresources pathways, they are limited by the production and treatment of sludge. So if we combine all of the maximum potential production from all of the bioresources pathways for all water companies, we generate a maximum possible hydrogen production of about 0.35 gigawatts, which is around about 7% of that 5 gigawatt target for the UK hydrogen economy. So what this tells us is that these pathways can generate a lot of hydrogen for internal use within water industry and for a reasonable amount of export. But if the water industry decides that it wants to operate at the gigawatt scale and be really ambitious, it will need the final effluent pathway. So for the ammonia pathway, there's a couple of both Severn Trent Water and Northumbrian Water independently have got innovation projects in this area. The real benefit of this is the benefit to treatment through the removal of ammonia. So this reduces load back to the returned back to the wastewater treatment works in sludge liquors, and can also have the co-benefit of reduced nitrous oxide process emissions through that reduction in load. However, as we can see here, we've got one little Lego brick, so actually has the lowest production potential of all of the pathways. Yeah, so just in a summary of there, lowest quantity, also relatively low in readiness. I mentioned could be done by electrolysis, could be done by thermal cracking. We don't yet know, neither of those are yet commercially available at scale. Reasonably flexible, because we could actually isolate the ammonia in a concentrated form and take it off-site and do the conversion into hydrogen elsewhere. So we could get an economy of scale and relocate that hydrogen production somewhere else that's where the hydrogen is needed most. And we also have the treatment and the carbon benefit through the removal of nitrogen load. So moving on to the ATT pathway, so this advanced thermal treatment. So this can be done either by pyrolysis or gasification. Both of those have been looked at by Yorkshire Water and Thames Water in the recent past, and hopefully will be ongoing in the future. It can be applied, as I say, to raw sludge or to biosolids that have been treated through AD. I've modelled it here applied to biosolids for a few reasons. We obviously already have a large asset base of digesters to treat biosolids as they are. We can get a benefit in terms of dewatering of digested sludge versus raw sludge, and that will help us when it comes to thermally dry the sludge before we put it through the gasifier or through the pyrolyzer, and that is a must. It needs to be up to about 90% dry solids in order to perform this pathway. Also, if we've destroyed some of the solids, the ATT unit itself can be smaller, and so we can reduce the capital investment required for it. And also, it means that all of our biogas operations are completely independent, and we get a moderate hydrogen production quantity for it. We do think it's going to be possibly the most capital-intensive pathway of all the pathways, and considering we only get a moderate production of hydrogen, why would we choose this pathway? Well, potentially it wouldn't be driven primarily by hydrogen production, but by new barriers to recycling of biosolids to land. So in the UK, as sure as we all know, we're heavily reliant on the recycling of biosolids to land. About 82% of the UK's biosolids goes to land, which is great, but it does mean that our sort of business as usual sludge treatment is kind of vulnerable to these new barriers, as we've seen this year and ongoing through the farming rules for water, but also potential future consents on sludge, on emerging contaminants in sludge such as microplastics and PFAS. So the ATT pathway through gasification or pyrolysis, they can tackle these emerging contaminants whilst being a net zero compatible alternative to incineration, which is typically associated with high emissions. So if we're forced down some kind of thermal route, we don't have to throw the net zero baby out with the bathwater, if you excuse that imagery. So we think that that's really why you might want to go down this pathway. I mentioned sludge thermal drying, so that is one of the also a large barrier to the ATT pathway. We heard it in the talk earlier on about the energy involved in that. We think actually once you get through the production of the syngas, you take it through a separation step, shown here as pressure swing adsorption as an example, PSA, to isolate our pure hydrogen. That also generates a reject gas or an off gas, which itself is still got a lot of calorific value, and we can actually recycle that. We think through this mass balance that we can recycle that back to the thermal sludge dryer, so that we can actually dry that sludge without being reliant on any natural gas or external energy requirement for that, which obviously is going to be important for the carbon balance of the hydrogen that you produce. In that case, it will require some kind of external power to provide heat for the pyrolysis, though, so i.e. through a renewable electric source. So in summary, moderate quantities, the moderate state of readiness are relatively low in the UK. There are some commercial operations outside of the UK at a reasonable scale coming online. Reasonably flexible because you can transport sludge a limited distance by road to a centralised location where the production of hydrogen might be a bit more strategic. And you have your treatment benefit in terms of your emerging contaminants, and a big carbon benefit because you're not going down an incineration route, which generates a lot of nitrous oxide, and you're also generating a really stable carbon biochar product, which could be sanitized enough to be recycled to land and stored in soils for carbon sequestration. So finally, the two pathways, I've kind of lumped them together, the SBR and SMR pathways. So these pathways are, within bioresources, are capable of producing the largest quantity of hydrogen out of all of the bioresources pathways. They're also unique among those pathways in that there's no sort of co-treatment benefit associated with these pathways. They're purely for the production of hydrogen. So what that means is that they can't leverage the viability of hydrogen production through some kind of co-treatment benefit. The viability rests purely on the shoulders of hydrogen production. So clearly, if we're converting some of our biogas into hydrogen, we can't continue using that bit of biogas in our usual ways that we would use. So the question could be, well, why would we go down this pathway? I asked myself that question as well, but there is some logic to it. So for the last 20 years, we've been incentivized in a water sector to use our biogas to generate renewable electricity. We've generated some biomethane as well, but most of it at the moment still goes down through combined heat and power through CHP. And these have been incentivized through the renewable obligation certificates. But from next year, we'll actually start to see an exponential decline in the number of those certificates that are still active. So actually by 2030, when we're hoping to be at net zero, 85% of those ROCs will have expired, and the last ROC will expire in 2037. So we will be losing that revenue stream relatively abruptly from next year for biogas. So it begs the question, well, actually, what else can we be doing with this biogas? Could we make hydrogen? Well, the obvious answer could be, well, what we make biomethane, which is fine. The new green gas support scheme will offer renewed tariffs for biomethane injection into the gas grid. However, there's a big caveat to that. It's only open to new build AD systems at present. So transferring AD plants from CHP or increasing the amount of biomethane that they produce, they won't be eligible for the scheme at this time. So that's actually a big barrier for biomethane going forward through the green gas support scheme. So if we can't put it into biomethane, what else could we do with it? Well, we could still generate, there are other schemes available for financial support. So for example, here we've got the Renewable Transport Fuel Obligation, the RTFO, and this is both biomethane and hydrogen are eligible for this financial support scheme. But potentially a really quite a significantly larger benefit for hydrogen per kilowatt produced than for biomethane if the hydrogen can be classified as a development fuel, which is quite a big if. How are we doing for time?
1 minute.
Oh, okay, perfect. Another big benefit of the SMR pathway is the potential for centralizing and relocating the conversion of that biomethane into hydrogen at a strategic location. So what we can do is we can actually inject the biomethane into the grid and take it out again somewhere else, and through a mass balance, using a mass balance, and then do that conversion at somewhere else where it's actually more strategic to do so, such as an industrial hub or a port, somewhere like that. And what this also enables us to do is to increase that economy of scale. So the amount of biomethane that we can actually produce at an STC relative to the amount of natural gas that a conventional SMR plant would use is actually tiny. So by doing this strategy, we could actually, the water industry could increase the economy of scale there. It also introduces the opportunity for flexible business models as well, because the water companies could own and operate that combined SMR plant in that central location, or it could just act as a supplier of biomethane as a raw material, and a third party does the actual conversion into hydrogen. So lots to think about there. Interestingly, the SBR pathway, because raw biogas still has that high carbon dioxide content, that can't be injected into the gas grid. So we don't actually have that flexibility through the SBR pathway. So just to sum those two, the largest amounts of quantity in the bioresources pathways. The SMR pathway, the individual components have a much higher state of readiness, technology readiness, than the SBR pathway, where they're still looking at it at the kind of development, at the demonstrator scale. Big flexibility for the SMR pathway over the SBR pathway. There's no co-treatment benefit for these pathway compared to the other the other options, and no co-benefit to carbon unless we introduce carbon captures and storage as well on top of that, which I've not gone into here because it's already a very complex area. But just to summarise then, the hydrogen. So this is a summary of the all of the pathways, including the final effluent pathway. So there's big benefits, but also big shortcomings to each of these pathways. There won't be a one-size-fits-all solution. In terms of the resources consumed, no surprise, electrolysis by the final effluent pathway consumes the most power. But actually, the other pathways also consume a considerable amount of power, either through directly through compression of biogas for upgrading and for the reformation itself, or because you're no longer using that biogas to generate renewable electricity. The ammonia pathway has a considerable heat demand, and this is to do with the thermal stripping of ammonia from sludge liquors. It's really important that if you do go down a thermal stripping route, that heat is from a renewable source. If you use natural gas for that, it obviously impacts on the carbon benefit of the hydrogen you produce. Finally, in terms of water, commonly the electrolysis route is cited for water consumption, what about water scarcity? But if we actually look across all the pathways, they all consume water, and some of them are a comparable scale or even more water than the electrolysis pathway. So I'm going to wrap it up there, if that's all right. I haven't got time to go headlong into the end uses section, which was a bit ambitious for me to include. I'm here for the next few days, so if anyone has any questions they want to bring to me outside of this session, or contact us, and keep an eye out for our the thought pieces that will capture everything in this talk and more. Thank you.
Thank you very much, Andrew. We have time for one, maybe two questions, which I'm going to take from the floor. If you're posting questions online, we'll get the presenters to answer you in person afterwards. But has anyone got a question from the floor? You please. If you want to say your name and your organisation.
Hi, Stuart Ainsworth from HAG. I'm just really great presentation. Did you go further with the actual different streams and plot kilowatt hours? So actually associate the energy of producing the yield of hydrogen. So you've got a specific kilowatt hours per kilogram of hydrogen for each of those streams.
Yeah, we did. So on one of the final slides I showed, we looked at the power there, where it's sort of in the ballpark of 50 kilowatt hours per kilogram for electrolysis, so for the final effluent pathway, and around about half that for the SMR, SBR, and ATT pathways for different reasons. They all consume energy, not as much as the electrolysis one, but actually still a reasonably large amount. And that energy needs to come from somewhere, and it needs to be certifiably renewable in order for the carbon benefit of the hydrogen to be realised, and also probably for any future or existing financial schemes to recognise the hydrogen as renewable and to get the full benefit of those financial benefit of those supports as well. But obviously twice as much for electrolysis than for the bioresources pathways, but they're still not insignificant.
Thank you.
Cheers.
One more question. Gentleman over there.
Hi, Dave Tompkins, Aqua Enviro. I've got two questions, but I'll restrict myself to one, and you may want to take a hospital pass on it anyway, which is absolutely fine. My question is about ammonia, and whether or not you've done any investigation into the energy potential of ammonia itself as a compound, as against converting ammonia to hydrogen, and what that might do in terms of options in future for energy carrier, energy storage, that kind of thing.
Yeah, so you're right. I mean, obviously, the ammonia itself is something that's recovered and is something that would have value. And actually, if you're converting it into hydrogen, you're going to consume some of the intrinsic energy within that ammonia in order to do that, form that. So it really depends ammonia as an energy source. It has, if you isolate it in a concentrated enough form, then obviously in an anhydrous form, for example, then you can transport that around quite a bit more easily. Obviously, ammonia with shipping and stuff is going to be important, so it might depend on the location at which your STC is. You can transport it a bit by road, but it's going to be limited. My personal view is that actually, and we have done some of the analysis on it in terms of carbon benefit, is you're already producing ammonia. We've seen the last few months ammonia plants being shut down because of the price of natural gas. We're recovering ammonia. It's already a valuable product. Possibly hydrogen isn't the best route for it, actually. In my view, it will depend on a case-by-case basis, obviously. And that still brings up a whole heap of problems like, classifying end of waste for that ammonia, making that into a product that farmers actually want. Kind of slightly dodged your question slightly by moving the focus, but No worries.
Great. Thank you very much, Andrew.
Thanks, guys.
Okay, we're going to move on to our next speaker. So we are running 5 minutes over because we started late. So we will be 5 minutes late into the break, but I think it's worth it to give the speakers that time that they deserve. So our next speaker is online, and it is Christian Torri from the University of Bologna in Italy.
Thank you, Chairman.
Great. To share your presentation.
Could you please make me the presenters?
The technical team will sort that out.
Thank you. Share my screen.
Yeah, please
Thank you,
start.
Chairman. Okay. The presentation will talk about the results about a project called B+ Demo that studied the production of polyhydroxyalkanoate from anaerobically digested sewer sludge. We started from two problems, parallel problems. One is that given the interesting features of plastic that is cheap and useful in several applications, nowadays we are using more than 400 million tons per year of plastic, different type of plastic. This plastic is characterized as used by good performance and low price. This means that it's difficult to substitute with bio-based plastic, in instance. The problem is that a significant portion of that plastic, namely about 6 to 8%, end up in the environment, and usually it ends up in the oceans and the sea, providing concerns on life and back to the human beings through the food chain. For these reasons, several authors, several policymakers proposed the substitution of at least a portion of that plastic, especially the portion that is usually unintended dispersed in the environment, in instance of single-use plastic, or the plastic that for some reasons, let's say in instance of agricultural used plastic, can be dispersed in the environment more easily. The problem of that approach is that if we plan to substitute a substantial fraction, in instance 100 million tons, this amount is quite larger than the amount that the actual production of bioplastic, that is between 2 and 4 million tons per year. This because bioplastic is more expensive, then it's difficult to substitute to the petroleum-based plastic, especially in the developing countries, which are in turn also the countries in which the unintended spreading of plastic occurs. One of the approaches to reduce the cost of the bioplastic is to use a waste. From that point of view, wastewater treatment sludge, more than 300 million tons on dry matter basis per year worldwide, is a good candidate given the fact that it's a material that is relatively standardized, is pumpable when it is a 2 to 8 dry matter content prior to the watering. And the issue of this material is that most of this is already something that is difficult to be utilized by a pure biological mean. This is because most is already anaerobically digested. Luckily, because this proves that a part of the material, a part of the organic content was already recovered as biomethane. In instance, in Italy, 70% of the sewer sludge is provided as anaerobically digested sludge because the plants, the wastewater treatment plant already have the anaerobic digester. Nonetheless, given the high amount and given the low availability of field for, in instance, soil application, the disposal cost is now between 90 and 180 euro per ton, which means a significant cost for the company that has the production of wastewater sewer sludge. Nothing news for the audience. The idea of B+ demo was to couple that two problems to create an industrial synergy between the wastewater treatment sludge production and bioplastic need. Then we coupled different known process. Here you can see the technology readiness level of the project we coupled to demonstrate at demo scale a first sludge to PHA pathway. Process coupled were hydrothermal carbonization, anaerobic digestion coupled with solid liquid separation with filter press, and aerobic microbial mixed culture that convert the soluble part to PHA production, and finally a newly developed extraction with green solvent. Here you can see a graphical description of the process as it appeared in the 2020 when we started the operation on the plant. The sludge is withdrawn from before the watering steps. Then we talk about a sludge with between 2 and 8% dry weight. Is subjected to hydrothermal carbonization, which deliver a hydrothermal carbonized slurry to an anaerobic digester with a residence time of 4 days. Then is a small scale anaerobic digested that produce a fermented slurry provided to a filter press that allow the separation of a dry HTC cake with a dry matter content usually between 30 and 50% dry weight and a clean fermentation broth. This fermentation broth is formed by a large amount of volatile fatty acid given the previously adopted anaerobic digestion and is provided to a sequence of aerobic pond in which in the first pond we have the growth of PHA producer, bacteria that are able to produce PHA. This is because the feedstock is provided by the so-called feast and famine mechanism. And finally, the produced biomass with low content of PHA between 10 and 20% dry weight overflow to the accumulation reactor in which the biomass is fed with a VFA-enriched flow, which means a solution in which we have just the COD without enough nutrients to grow. In instance, if we have as limiting nutrients the phosphorus, we have to remove the phosphorus in that case. This is the first configuration we studied during the first year. The bacteria obtained by the aerobic section is finally separated by means of a centrifuge, and finally the slurry, 20% dry weight slurry, which is already pumpable, is something similar to a yogurt, is extracted with a solvent, dimethyl carbonate, which is a grease solvent we developed for PHA extraction in a the final extraction section that continues to produce the PHA. Here you can see how it appears in the reality. The plant was designed, built, and installed and operated in the Caviro Extra premises. Caviro Extra is a distillery that expanded its capacity for sludge treatment by including sludges from several food and beverage manufacturing company in Emilia-Romagna region, with a total throughput of sludge of more than 500,000 tons, which then it make Caviro a sort of biorefinery for sludge. Here you can see the results of the operation of 2020. Operation starts in May and ends in December for a re-evaluation. We started exactly at the end of the hard lockdown in Italy during 2020. It was very strange time, and it was the first time we come out from home for running the plant. And here you can see the input sludge that is similar to several thickened sludge, 20 grams per liter total COD, a minimum amount of soluble COD, given that these 3 grams per liter of soluble are formed half by ammonia, which is quite high. It's about 1 to 2 grams per liter of ammonia because the sludge comes from anaerobic digestion. The HTC was able, as in small-scale experiment, to deliver about 50% of the total COD as soluble substances. And finally, the slurry provided to anaerobic fermentation demonstrated able to convert half of these soluble substances into volatile fatty acids, arranged between 40 and 75 variable amount of the soluble COD. Then the final fermentation broth obtained after solid liquid separation showed a content of VFA between 6 to 10 grams per liter VFA, volatile fatty acids, about 3.5 grams per liter ammonia nitrogen, and about 100 milligrams of phosphorus per liter. Looking to the balance between nutrients and COD, we had a ratio that is similar to that we need for the grow reaction. Then we provided such broth as it is to the biomass grow reactor, and after phosphorus abatement or using synthetic simulated water in the accumulation reactor. Here you can see the process that used a pilot filter press for solid liquid separation, at the end, pilot filter press for solid liquid separation, allowed the obtainment of 37, this is the average value, but it was quite constant with the months, dry matter cake. This is quite high. Consider that sludge with the PET that is now following in the Caviro extra premises, then addition of polyelectrolytes, and finally solid liquid separation with centrifuges, with decanters, usually provide a dry matter content of the water sludge between 20 and 23%, no more than that, with a large amount of polyelectrolyte used. Instead, we were able to obtain 37%, also in presence of the solubilization of a part of the substrate. Then this suggests that in terms of disposal strategies, the STC anaerobic digestion system works in excellent way. That fermentation broth that consists of a reddish liquid, relatively clear of solids, it resembles a dark beer, was provided to aerobic fermentation with the mixed microbial culture, providing a VFA to PHA yield of between 10 and 20%, and a PHA content between 20 and 30%. Both data were lower than expected and lower than literature. Let's see after why, or why in our opinion. Finally, this biomass was separated and subjected to our solvent extraction performed at 120 degrees in a pressurized extraction with DMC with our equipment, and it provided a polymer that was similar to that obtained in the lab. Here you can see in the picture the gel that we obtained immediately after the cooling of the mixture, the extraction mixture. Immediately after the cooling, the DMC is quite interesting because it is quite affine to PHA, and then it forms instantaneously a pumpable gel that is finally dried to the clean PHA that all again retain a very high molecular weight. These 4 megadaltons are quite high in the PHA context. Then we went through the reasons why we obtained such underperforming operational results, and moreover also because we obtained a PHA concentration relatively lower than expected. This also has some implication on the extraction sites because it's more difficult to extract a biomass when we have less than 30% dry weight PHA. What we observed by a detailed monitoring of the system, we observed that in the reactor 1, in which we supposed to have growth, we observed a relatively high VFA to PHA yield and a relatively high max PHA content. We obtain high pH in the wrong place. Instead, in the second reactor, that was supposed to be the PHA accumulation reactor, we observed a VFA to PHA yield lower, as I showed before, and a PHA content that decreased. This was very strange because we used a configuration that was very known in literature. Then we looked into the specific features that were different from the lab, because in the lab we know that something should occur, but in the plant scale, in the demo plant scale, we observed a totally different behavior. If you look to that trend expressed as yield of COD in terms of COD of certain product with respect of COD of VFA provided, you can see that sometimes it reaches 100% or more, because you should consider that a part of COD is not VFA. Then if this also is consumed by the bacteria, we can obtain very high COD yield of biomass and PHA, but especially of biomass. And what we observed that first, that we have very variable trends, and that very variable trends in the beginning were expected, because usually is known in the literature that microbial mixed culture require about 3 months to reach stability. And subsequently, we observed again this situation in which we observed that PHA concentration in SBR cycle was quite high. Instead, the biomass actually grows in the accumulation reactor, and the cause of the decrease of PHA was the dilution due to the biomass growth. We put together this information with the other 2020 demo features, given the season in which we performed the demonstration. One, that we had, unfortunately, very low oxygen concentration during feast, especially due to the extraordinary hot heat wave in the August 2020. For about 20 days, in instance, we observed more than 35 degrees in the water, which is something which is similar to mesophilic condition. It's something completely unexpected and completely different from the lab scale. And after this heat shock, and in September, when we obtained the peak in PHA production, here actually, we make the molecular analysis of bacteria, and what we observed that we expected to have mostly Azoarchus, Tawera, and Rhodococcus, which were the inoculum and which dominate the lab scale system for years. We observed more than 85% Azospirillum genera, and probably a single species, but we didn't investigate in detail that one. 85% in a mixed culture is something that is similar to a monoculture. It's quite striking. Then we looked into some details about this genera of bacteria and about some of the reasons of this strange behavior, in which we observe high amount of PHA in the different place. One of the hypotheses was that we performed, without wanting it, aerobic anoxic cycling. That cycling was already proposed. In the past, in the PHA research, there were several approaches. The first one was the aerobic anaerobic cycling, in which bacteria store temporarily the energy into polyphosphate or glycogen, and through polyphosphate hydrolysis or through glycogen glycolysis, they can generate energy for storing PHA during anaerobic condition. This is very known in the wastewater treatment field, but it will never demonstrate the production of PHA more than 20%. Then it's not the case. Nonetheless, we found that Sato et al. In the last decade of the previous century identify a different PHA accumulation strategy in which we don't use completely anaerobic system, in which the limitation is the amount of polyphosphate or glycogen we can have in the bacteria, but microaerophilic system, in which actually we have the stress, but we have also a minimal amount of oxygen that allow the bacteria to replenish the storage of polyphosphate or glycogen, but that disadvantage the growth of bacteria. This is an interesting feature if proven, because we observed, in fact, looking the first single reactor, taken as it is, it was something in which we provided the broth as it is without any correction of the nutrient COD ratio, obtaining a pHa yield and concentration enough for the extraction and for our process. Then we passed we performed during the first year, the first month of this year, some small scale tests at 5 liters scale, in which we compared the two situations. One was the initial B+ process, which was fully aerobic, with aerobic feast and famine, followed by a VFA last feast. It means that the bacteria withdrawn from the growth reactor are provided with additional VFA, just VFA flow without nutrients. And this proven to be okay for producing the amount we needed of pHa, and we observed in small scale again what we expected in the large scale. Then we proved that this strategy is feasible. But beside this process, we tested also a system in which we have the aerobic feast and famine cycling, but instead of providing just VFA, we provided the fermentation broth as it is, but with this anoxic system, or less than 30-60 milligrams of oxygen per liter per hour. These provide us exactly the same results we obtained with the VFA last feast. This is very interesting because it's a simple process. Then we used these findings of the first year to slightly modify the process and create the B+ demo revised process, in which we just recycled the biomass and we contact the biomass with the broth in a first section with microaerophilic conditions. Here you can see the same trend I showed before for the amount of biomass that exit. We don't have anymore the separation between the two sides, because we just sample the biomass coming out from the microaerophilic condition in which we collect the biomass. And the result was quite promising, because first we obtain a stable system, a relatively stable system. Here you can see the first days. I didn't update with the last 2 months because we deeply analyzed just that one. But in the last 3 weeks, in instance, that is a relatively long time for microbial mixed culture, what we obtained is that we have a stability around one of the last point of this graph. Here you can see how they appear. You can see that in the beginning we have that biomass that has oscillates between 10 and 20% pHa as previously, because actually is identical to the previous steps in the aerobic part. And finally, we have the anoxic part. You can appreciate that is anoxic even by the change in color and in the change of settling behavior, because when we send the bacteria and they go in the microaerophilic system, they lose the structure they have before, with about 35%, which is the average concentration pHa. 35%, especially given the high yield beside the concentration of pHa in the biomass, is suitable for extraction. Therefore, summarizing up the results of the new test that now has the same length of the test of the 2020, we obtained a VFA to pHa yield, this time 20 to 30%, then slightly higher, 50% higher, and comparable with the literature. Consider that we are working with an unoptimized system. This is quite promising results. And the pHa content still quite variable, especially because the mechanism of microaerophilic was created in the plant with some solution that we were able to adopt during the 2021, but was not exactly designed for it, between 25 and 45%. Finally, the extraction, thanks to the increased amount of PHA in the biomass, as expected, improved a bit. But anyway, the performance is quite similar. Here you can see the picture of the gel. Here you can see the gel is a bit more solid because the amount of PHA in the gel is higher. And here you can see the biomass, the PHA as it appears as soon as you dry out the methyl carbonate without cleaning with the subsequent process that is sometimes needed. Moreover, since one of the interesting things of the practice of the plant is to see exactly how it appears, here you can see the bacteria in the aerated pond that are exactly like the activated sludge of a wastewater treatment system. Here, after the solid liquid separation, this is the paste that is subjected to extraction. It's a paste between 10% and 20%. Actually, we observed that 10% is probably better for the extraction, and we have not a large increase of solvent losses because of special features of methyl carbonate. And finally, the product we obtained. In conclusion, B+ demo performed two campaigns, two experimental campaigns, that one of it is still ongoing. We demonstrated that resubstrate, anaerobically digested sewage sludge that was never used for such purpose, was used for a completely mixed microbial culture system for PHA production. Anoxic aerobic cycling successfully produced PHA more than 45%. Very important, without carbon and nutrient decoupling, without COD and nutrient decoupling. Usually, all the process until now require that you adjust the nutrients. If you have an excess instead of nitrogen, it's not an issue, but you should remove all the phosphorus, at least most of the phosphorus. Of course, it can be done very easily because consider that if you remember the slide before, the amount of ammonia is quite high. After the digestion, then is enough to just add a source of magnesium to precipitate or just to correct the pH is enough. We use the broth as it is. The STC to VFA yield was between 16 and 25%. This figure probably cannot be improved so much. It just depends on the biodegradability of the material after STC. It can be improved probably by tuning STC, but probably not so much. VFA to PHA yield was comparable to the literature, then it was suitable for the commercialization. The only issue that remains on the table is that we still see a variable performance, and probably this should be fixed by a more strict monitoring of the process. That is something that is ongoing now. And finally, very important, because if you remember, I show you the path of TRL we planned. It was the less mature part, the extraction, I mean. The extraction proven to be challenging, of course. It can occur with the high effectiveness just when we have more than polyhydroxycanoate content in the dry matter of bacteria, but it's feasible. And for the first time, we have a machine bring it to the lab for the extraction, as in most of the previous projects, but we realized that a small plant that is able to extract the mixed culture PHA. This is quite interesting because there are several initiatives and several demos in Europe and the world that use different microbial mixed culture on different substrates, in instance food waste or other substrates, to produce such material, such bacteria enriched with polyhydroxycanoate. Given the feature that our extraction doesn't require drying of the bacteria, but we directly use that paste you see in the middle of this slide, this extraction system can widen and can improve a lot the applicability of mixed microbial culture, because we have a way to get out the BHA in different conditions, and even if in the system which they just modify wastewater treatment plants to produce more PHA in the biomass. On such purpose, what we have to keep in mind is that we are able to extract PHA just if the PHA is more than 30%. This is a limitation. We should have a relatively good biological process to produce such biomass. Nonetheless, the process is now under long-term demonstration by the spin-off company B+, and you can find a lot of new information and updated information and more detailed information in the website of the project and in the website of the company B+ SBRL that is now working on this. Thank you very much.
Thank you very much, Christian. I'm afraid we don't have any time for questions unless someone from the floor here has some quick burning question. I'm just looking around. Please do contact Christian using the Hopin platform, and I'm sure he can answer any questions you might have then. So we're off to a break now. Please be back at 11:30, either to this room or room 1 over there. Thanks, everyone.
Good afternoon, everybody. Welcome back from lunch. And thank you for being at the session. I'm replacing my colleague, Paul Lavender. My name is Danny Traxel. I work for Royal Haskoning DHV. This is actually my first time in Newcastle. And I'm from Holland. So, and I have an association with Newcastle. Two things I associate with Newcastle. One, Alan Shearer, who is has always been a pain for the Dutch soccer team. and the second one is Bobby Robson, because I sponsor a team. My favorite team is PSV. And of course, Bobby Robson has always been a great trainer for PSV. And Bobby Robson always had one player that he had great trouble and challenge with, which was a Brazilian player, Romario. And he was able to manage this pretty difficult player. And it actually became one of the greatest soccer players in the world. Look at the World Cup 1994 in the USA. I think he was top scorer. So that's my association with Newcastle. And I see resource recovery also a little bit like a Romario. Difficult to handle, but it has great opportunities for the future. So everybody, welcome to the session. And I'll give the word to Maria. Maria Dietman from Elico Technologies. And she will talk about operational experience with vacuum degassing of digested sludge with integrated phosphate participation to avoid struvite scaling. Up to you.
Okay, thank you. A very complicated title. So thanks for the opportunity to talk here today. As Danny said, my name is Maria Dittmann. I work with Elico, and Elico provides solutions for municipal wastewater treatment. We have several entities in Europe, that is in the UK and the Netherlands and in Germany. So I am based in Germany and also work closely with my colleagues in the UK. And the focus of my work is carbon neutral and efficient sludge treatment technologies. And one major part of that is our ELOVAC technology, which is vacuum degassing of digested sludge. Vacuum degassing can provide several different advantages for sludge treatment. And today I'm going to show you some practical results from trials that we did in Germany. And the focus of that is vacuum degassing with integrated phosphate precipitation, which is a key to net zero carbon and also to avoid struvite scaling. So to start off the presentation with a glass of sparkling water may seem unexpected, but we like to use analogies to show what really happens in the digested sludge. And if you look at the glass with sparkling water, normally the gas bubbles escape from the liquid to the gas phase very freely. But then if you put a straw in the glass, the gas bubbles adhere to the surface and are hindered to escape. And actually something very similar also happens in the digested sludge. So the biogas that is produced in the digesters adheres partly to the solids in the sludge, and not 100% of the biogas that is produced in the sludge also is captured in the biogas system. And these entrapped biogas bubbles then escape to atmosphere in the following sludge treatment stages, so in the sludge storage and also during dewatering. And if you've listened to the previous presentations prior lunch, I think we meanwhile know the relevance of methane emissions in terms of the impact as a greenhouse gas. So especially over the short term, over 20 years with a factor of 84 CO2 equivalent emissions, avoiding these emissions really is one key to achieve net zero. And one way to avoid these emissions following the digester is ELOVAC, our vacuum degassing for digested sludge. And if with this we can, in a targeted way, capture the residual gas which is still present in the digested sludge, and if then this biogas is fed to the biogas system and utilized, we even have an energy positive operation, so that means we can produce more energy than a vacuum degassing itself needs. And as mentioned, that's one key step to net zero to avoid these greenhouse gas emissions. And then we have an additional option, and that is to add integrated phosphate precipitation. That especially makes sense for wastewater treatment plant with elevated orthophosphate concentration. So that's, for example, with biological phosphorus removal or with advanced digestion. And by adding this additional step, we can achieve further benefits on the operational side, additionally to the ecological benefits. And that is, for example, improvement of dewatability and also mitigation of struvite scaling. And on the struvite scaling part, I will get into more detail in the second part of the presentation. And for that combination of vacuum degassing and phosphate precipitation, we also have a patent pending. And one of the key features of ELOVAC is also that it's really a very compact and plug-and-play unit. So on the right side of the slide, you see a 3D model of a plant that has a capacity of 20 cubic meters per hour. Yeah, you really see it's 2 meters times 5.5 meters. So it's for a mid-sized treatment plant, that's already a sufficient capacity. And actually also the same size that we have for our demo plant, which you will see pictures later on in the presentation. Then how does ELOVAC P works? So basically it looks pretty simple. If it gets more complicated if you look at the details, but in principle, the digested sludge is continuously provided to the degassing reactor tank with a progressive cavity pump. And then in the degassing reactor tank, negative pressure is created via a liquid ring vacuum pump. And via this pressure, we capture in a targeted way the residual biogas, which is on the one hand microgas bubbles, but also dissolved biogas. And then in this degassing reactor tank, we can dose simultaneously magnesium chloride solution to enable a controlled phosphate precipitation. Because with the vacuum we not only withdraw methane, but also CO2. And withdrawing CO2 increases the pH. And the elevated pH, together with the magnesium chloride dosing, is the perfect environment for controlled struvite precipitation. And then on the right side, you see where ELOVAC P is implemented directly after the digester. There, it's perhaps important to note that ELOVAC should be implemented in such a way that the digested sludge is not exposed to atmosphere before it goes into the vacuum degassing, because already when the digested sludge gets into contact with the atmosphere, the partial pressure in the gas phase is lower, and then already, for example, at a wear box, the methane starts to escape, and there are several possibilities to enable this, and we are also happy to support there on specific solutions for treatment plants. And perhaps just to clarify, so ELOVAC is the vacuum degassing itself, and ELOVAC P is then the combination with simultaneous phosphate precipitation. And then to get to the practical part of the presentation. So last winter we did full-scale tests with our ELOVAC demo plant at the wastewater treatment plant in Hanover in northern Germany. The design size of the treatment plant is 500,000 population equivalent, so for Germany that's pretty big. And the duration of the operation was 4 months. In last winter, and the demo plant has a capacity of 18 to 20 cubic meters per hour, and that's also the reason that we call it demo plant and not pilot plant, because it's actually a full-scale treatment, and the full flow of the treatment plant was treated during the trial. And you see also a picture here of our demo plant in the last year. So we built it in October 2020. And in the last year, we've really been traveling a lot with the demo plant and collected a lot of experience. And I think also with this demo plant, we could really prove that compact and plug-and-play character of Elovac. So for example, in Hanover, the plant was set up, installed, and commissioned all in one day. So that was pretty simple, and it only needs electricity and water for operation, and then magnesium chloride solution if phosphate precipitation is required. Then for the project goals of this project in Hanover, the first and also most important goal was to avoid the severe struvite scaling in the connecting pipeline between the two wastewater treatment plants, Herrenhausen and Gümmerwald, because all the sludge from Herrenhausen is pumped through a connecting pipeline that with a length of 13 kilometers to Gümmerwald for dewatering. And in case you don't know what struvite scaling looks like, this is what it looks like. And so it's a deposit that consists of magnesium, ammonium, and phosphate, and it's really hard to remove. And this is not something that you want to have in a 13-kilometer long pipeline. And therefore, this was really the main driver for the project to avoid this struvite scaling. And then additionally, they wanted to improve the dewatering to save on sludge disposal costs and, of course, avoid greenhouse gas emissions. And our project partners were the Stadtentwässerung Hannover, who operate the treatment plants, and Kläranlagenberatung Kopp. And then here you see how the operators are currently dealing with that struvite scaling in the connecting pipeline. On the right side, you see these pigs, you may know perhaps. So normally, initially, they are red, and then after passing the pipeline, it's not so red anymore, because by passing through pigs with a high pressure through the pipeline, the deposits are removed. And deposits in the pressure line cause the pig to move unevenly by sticking and loosening, and that causes then this abrasion on the pig. And this is also the assessment parameter that we used to see how successful our trials were. Because the loss of the volume of the pigs, this is something that you can measure by just measuring the size of the pig. And the lower the volume loss, the lower the abrasion, and the lower the struvite scaling. So here you see the volume loss on the y-axis over the time. So in the first half, without Elovac operation, it was at around 3 liters volume loss, even partly as high as 4.5 liters volume loss. And then after commissioning the Elovac P, that gradually reduced. So with the lower volume loss, we could also see that there was a lower abrasion going on. Also, the pressure peaks were evaluated, but that gave similar results. So to make it easy, I just put here the volume loss, which is, I think, the more practical approach. And in the end, after a few months of operation, we could reduce the volume loss to as low as 1 liter before and after the pipeline. And you also see this from the pictures. Initially, there was quite some visual abrasion also, and in the end, this looked already much better. After we also optimized some parameters at the plant itself, like the pressure and the dosing factor. So you've now seen that there was a positive result on avoiding struvite scaling with Elovac P, but why is that? So therefore, here's some background on how struvite scaling occurs. So generally, if there is a low pH and a lower orthophosphate, there's an area with a low struvite crystallization potential, because these are the two factors that mainly impact the struvite scaling. And then with high pH and high phosphate, there's an area with high struvite crystallization potential. So initially in Hanover, we were over 200 milligrams per liter of phosphate. which also explains the Struweit scaling. And then after the ELOVAC-P treatment, we could reduce that phosphate concentration and even reduce slightly the pH, and therefore are in a very safe space concerning Struweit scaling. And so that's the first part of background on avoiding Struweit scaling, and the second part is you see here, or you barely see it, because it's the very small micro Struweit crystals. We had extensive tests done to wash out these crystals and filtering and everything to extract them from the sludge, which was still really hard. They are in a size of 10 to 35 micron. And this is also the reason why they stay incorporated into the sludge matrix and they don't settle in the sludge pipelines, and therefore don't cause problems in the sludge treatment. And perhaps also getting back to the point of nutrient recovery. So our goal is not to create big crystals which can be separated from the sludge, but really to have them very small so they can stay in the sludge, also during dewatering. And then if, for example, the sludge is land applied, in the end, you have Struweit, which is a slow release and highly plant available fertilizer in the sludge, which improves the biosolids quality. And even if you think about incineration, which is the main road in Germany, and then you have to do P recovery from the ashes, it's easier to recover Struweit ash than ferric phosphate ash. So that's also a positive note on the recovery of the phosphate. And here you see some microscopical pictures, and the red arrows indicate the Struweit crystals. And as you can see, you can barely differentiate them from the sludge matrix. Then, as you perhaps remember, we had also a second goal in the test, and that was improvement of dewatering. They had rental centrifuges to test this in Herrenhausen. And we had an increase of 1.8 percent points. And as the disposal costs are really high in Germany, every percent point counts to improve this. And for the treatment plant Hannover, this corresponds to 200,000 euro of savings per year. And then in corresponding to that dewatering results, also the polymer consumption could be slightly reduced by 1.4 kilo, which is 12% savings. So then ELOVAC-P in summary in Hannover, we have 4 parameters for the assessment. So that's the operational stability, and then our 3 goals, which is protection of the long-distance sludge line, influence on dewatering, and climate protection. On the first point, we had 16 weeks where ELOVAC was operated in a stable way without any major disturbances. Then so that's a check. Then on protection of the long-distance sludge line, we had a significant reduction of the Struweit deposits, and which is especially important for us is that for the first time we had a quantitative assessment to avoid Struweit scaling, because this is something that you have the feeling you have to remove it more often or not, and now we had a real parameter where we could measure it and also show it, and this was really important for us. And of course also for the treatment plant Hannover to decide on how they want to progress. And then on dewatering, we also had a positive influence of 1.8 percent points while reducing polymer demand, and also against H2S and Struweit crystals, previously 40 liters per hour of ferric chloride were dosed. And this could be reduced to 14 liters per hour, which corresponds to savings of 232 cubic meters per year of ferric chloride solution. And then on climate protection, by the operation of ELOVAC, direct climate damaging methane emissions could be effectively avoided. In this case, this corresponds to 92 tons of CO2 equivalent emissions per year. And then to close off, I just wanted to show you our reference overview. This also includes our full-scale demo plants because it's also full-scale treatment. And I'm actually really proud that we could make this list so long meanwhile, because initially everything was going a little bit slow. But now we really see things taking off. And I think that is not a coincidence, because net zero is really something that initially was something when we talked about, everybody said, okay, that's nice to have, but I don't pay money for this. And I think now the discussion is really going somewhere where this is really one of the key targets for treatment plants. And also I think the recent discussion in Glasgow, which puts a specific emphasis on avoiding methane emissions as a short-term lever against climate change, is something that Elovac can address by avoiding methane emissions after sludge treatment. Okay, so thanks for listening, and I'm happy to answer your questions. You'll have my contact details here, and also Neil's contact details, and we are also happy to talk to you at the booth afterwards.
Thank you, Maria. So, who wants to be the next Romario? Questions? No questions? Let me walk all the way up there.
First of all, thanks for the presentation. Very impressive result. I read that you have increase in the dry solid content of 1.8% when you use this technology. But do you have any idea of what kind of mechanism is behind this? Why does this dry solids content go up when you use this?
So I think there are two different things why the dry solids concentration goes up. One is the vacuum degassing itself. So if you have entrapped biogas that hinders the solids to settle properly in the centrifuge, and therefore by vacuum degassing, this is one part. But I think the bigger part is even the phosphate precipitation. So phosphates increase the water binding capacity of sewage sludge. So this is also something that's been examined, I think, in different studies, the correlation of phosphate concentration and dewaterability, and therefore that's also the second part of that increase.
Any other questions? That's close.
Adrian Mercer from Jacobs. What sort of increase in recoverable biogas volumes do you estimate?
In Hanover, they have a conventional digestion, and in that case, the biogas is generally in that case, it was between 150 and 200 liters of biogas per cubic meter of sludge. With advanced digestion, that can be much higher. So the highest values that we've seen is like 600 to 800 liters of biogas per cubic meter of sludge. As a percentage of the total biogas production, that's generally in a range of 1 to 3%. I think if you're thinking about increasing your biogas production, this is not like the biogas boost, but at least it's sufficient biogas for energy positive operation. I think that's also a good thing. And the focus is really on also avoiding these methane emissions as a greenhouse gas.
Okay. Thank you, Maria, again for your presentation. Okay, next is Matthew Gibson and Andrew Rushworth of Orrech. I'm saying that correctly? Nearly. Okay. I have an excuse that I'm not English, so. And they're going to talk about innovative sludge thickening package plant and its contribution to net zero in sludge handling. So up to you guys.
Thank you. Thanks, Danny, for chairing the session. Bit of an Ajax man myself. Thanks for everybody for attending as well. My name's Matt Gibson. That is the easy bit. The company name is Orrech. but we answer to Arage, Origi, all different forms. It's a French company. Headquarters is in Versailles. We've been in the UK about 5 years now. A bit of a background on just myself. I've been in the UK water industry supply chain for about 30 years. I was MD of Ashbrook Simon Hartley for 10 years. And then for 8 years, I was global sales manager for Alfa Laval for sludge thickening and dewatering, and worked in about 60 countries with Alfa Laval. In fact, it wasn't until the pandemic struck and we had to work from home that I realized I owned a dog. It was away from home that much. I joined Arege 2 years ago with impeccable timing as International Business Development Director just before the pandemic hit. And so myself and Andy have been working in the UK, and the international business has been Scotland and Wales for the last 2 years with our technology. Package plant isn't really innovative, so why are we doing a talk on innovation? It's the actual technology that Arege have developed and introduced that's the innovative part of this. And what we've been doing in the UK is installing mobile and fixed enhanced sludge thickening systems. And Andy will come on to some case studies a bit later in the presentation. SLG is very technical. It stands for solid liquid gas. That's it. SLG, solid liquid gas. And we'll try and explain that here. And I don't know if we'll be able to get that video to play with this control I've got there. There is actually a video there. But the SLG effect, we inject air into this feed sludge. And it goes against, it may be loud. Oh no, the nose is down. This is one of the installations that we've got in the UK. And what we do is inject air into the feed sludge with polymer, and it does everything that you don't want a sludge to do at first glance. It floats. Nobody wants a floating sludge, or they didn't. We want a floating sludge, because when that sludge floats, it allows for the chemical and mechanically bound liquid to be removed very quickly in a very small footprint machine called a flow sep. So that floating sludge there is the innovation. We pass the floating sludge over a stainless steel wedge wire drum. And when I say over, unlike a conventional drum thickener, it doesn't pass through the drum, it goes over the top of it. So it's a very, very small footprint that's required. And you'll see, again, when Andy shows you some of the examples from the UK, how small this is. So this is the, excuse me, I'm just going to have to blow my nose away from the microphone. Sorry about that. This is the current industry practice in the UK that we're all familiar with. So we have fleets of tankers transporting to the sludge treatment centres, if they're open, and accepting imports. 95% water, sometimes it's 98% water. And every water company does it. And so we saw an opportunity to market our equipment to reduce carbon footprint, initially to reduce the number of tanker movements. But we'll come on to why the innovation with package plant has sort of developed since then, when you consider it against traditional design and build sludge thickening installations. So associated with that model is high transport costs, CO2 from the lorries, high carbon footprint. There's fewer people on site. You need storage tanks. And what we've seen when we put the SLG and the flow sep on site, often on sites where there's no existing sludge thickening, on trickling filter, humus sludge sites, remote sites, that we can reduce the tankers by up to 70%. So there's 70% fewer tanker movements to the larger sludge treatment centres. And if we're at 6%, we can get it higher than 6%. And again, Andy will touch on that when we come to some of the examples. the return on investment has been pretty low for some of the water companies. So yeah, we're new to the UK, but I think we've got installations now, or we've demonstrated even during lockdown. We got on site with 5 or 6 English water companies. So I think there's only a couple that we've not actually managed to demonstrate the technology to, and the benefits you can see there of the reduction in the lorry movements, the return on investment for some of the water companies, the costs for the transportation for water companies fluctuates enormously depending on how it's costed. They've all got a different way of costing, whether it's in-house, whether it's outsourced, whether it's going 10 miles, whether it's going 50 miles. So that's why there's a variation on the ROI, on the return on investment, because it's amazing how much that cost varies between the different utilities. My next button is not nexting. Oh, there we go. And to give you some, I'll hand over to Andy now, and a colleague, Andy Rushworth, and he'll take you through some of the package plant advantages and some of the case studies that we've got within the UK.
Thank you, Matt. I think we all know the traditional design and build. We put down a concrete base, we put a kiosk up, we procure MCC, polykit, cost $1 million, $1.7 million, $2 million. And a lot of these smaller sites warrant thickening to do away with the tankers and the ICO2 that they produce. There are thousands of small sites, and I can talk about many of them in the different utilities. But they all tanker sludge from between 1 tanker a week to 5, 10, 15, up to 40 tankers a week, leaving some of these sites. And absolutely, they want thickening, but they're cost prohibitive. You just can't get thickeners on all these sites. So what we did with the technology, because we can do it in a very small footprint and do it well, we went down the package plant route. This was driven by a lot of the utilities. And there's one utility that specifically moved quickly with this and adopted and installed, and that was Scottish Water. They accepted that they were going to have to think out of the box in how they procure, asset standards, otherwise they're never going to meet their targets of net zero. So that's the way this went. So we developed the package plant, and I'll go through the 2 or 3 different formats that it comes with shortly. I'll flick through some of these slides because they're just explaining quickly what we've built in-house when it comes to engineering, design, the capability of Arage. Again, built around the client need to get thickeners on all these smaller sites and reduce the tankers. So it's a simple, robust solution that we manufacture and pre-commission in-house. So that allows for a speedy, quick, safe project delivery on site. Design and engineering, again, that's done in-house. So it's a simple process, site survey, which we can do within an hour of being on site. Then we can come up with a package. Most of these are off the shelf, though typical lead time may be 3 months, but most of these are off the shelf. And I'll go into a couple of case studies in a second, where they would basically order received, within a week it was on site and commissioned within 2 days. So that again is the purpose of the package plant, is to reduce cost and CO2 in both the way it operates and also site time project delivery. In-house installation and commissioning. So typically the project shows short. The installation engineers and commissioning engineers will be on the site in the same day, because typically this will be up and running within 1 or 2 days of arrival on site as a package. This case study, Montrose. Again, sorry, it's a busy slide, but it's a Scottish Water site on the coast, saline intrusion. So they pulled out the traditional drum thickener and installed a skid SLG 20 cube an hour. Because of the SLG process, we were reducing H2S, we were reducing slightly the ammonia and also the P. I can go on to the dynamics of that later on if you want to see me afterwards. So again, a very quick project, 8 to 12 weeks delivery on site. Day 2 it was connected and running. Day 3 wet commissioning and training. So that project actually on site, physical site time, became a 4-day project. It was up and running the second day. So from project delivery, it's reducing site time, cost and CO2, which is significant. If you look at site time on traditional DMB, archaic, we've always done it that way, you're talking weeks and months on site. You've got bat wardens, badger wardens, nothing wrong with those guys, doing site surveys, multiple cars backward and forwards from site cabins, you name it, you've got it. The CO2 is immense and cost. So let's look at package plant. How can we reduce that burden? And you've got to think out the box. You can't go down that same route, otherwise you're never going to get there. Similar project again. That is Aberfeldy, Scottish water site. They wanted a container with a carbon filter on the roof, but there's no odour anyway because we reduced the odour, but they wanted that. So again, we removed, I won't say the competition's here, so we removed an existing shipping container with an incline thickener in it. That again was down to one or 2 days. It was offloaded on site, it was connected the same day, running the next. One contractor on site, that was us. All the pipework was already in place. It was a simple plug and play and connect. Significant cost and CO2 reduction in the project delivery there. We can thicken up to 7, 8, 10%. However, Scottish Water are quite happy with 6 or 7. We add air, so we lower the viscosity. So they can still tanker and suck it at 6, 7, 8%. There are a number of other case studies I have with the UU and a couple of others that I'll show you, or I can talk to you about later on if you like, as to the dynamics of that, how that works. So again, another site, and these all came within a period of perhaps 12, 18 months. Very quick. This one, again, is an order we just received on Friday, actually. This is a site at Dalscon. They want mobile thickening to tow between 4 sites, but 2 initially, Castle Douglas and Dalscon. The author of this case study is in the audience somewhere, or is with us, Jamie, Scottish Water. So if you have any questions or you want to have a look at that, then please talk to him. So we trialled it there, we've put the money where the mouth is, and we delivered just that. The results there were extraordinarily clear filtrate, sludge up to 8, 9%. Not only does it reduce the tank space, it also reduces process and tank space on the reception site. So it's a double whammy. And within being able to de-sludge and process that site, which is a mixture of trickling filters, lamella, and a ditch. So we've got multiple sludge types there, but it just levels the playing field, does SLG. So that, again, with it being mobile, will be a 1-day delivery and commissioning the next day. It's imminently due in the UK, is that one. Finally there for the case study, interesting. This is Inverurie, Nereda site up there. They have 2 solids technology thickeners, shouldn't name them perhaps, but anyway. 2 solids technology thickeners, a bit of a bottleneck. So we pulled one out and put a skid in. Again, it was a couple of day project, probably 4 days, including the training. So it was in and operational within 2 days. Connected to existing services, and away it went. But again, and we have a number of studies there. What we see typically with the process, Pierce Clark refers to it as a DAF on steroids. With injecting air into the moving sludge mass, what we've seen typically, and we don't sell it on this concept, it's all about tanker movements, reducing the volume of sludge. What we see specifically is P 1 to 3% lower points, MGL, in P, but also between 3 and 6% in ammonia. The dynamics of that, again, I can talk to you afterwards. Air stripping, it's got to be air stripping. And P, the air precipitates the P into the sludge where it needs to be. So, again, does it have an effect on site compliance? No. Site specific, we do need to try it and prove that concept. But typically when we've run it side by side with a belt or a drum, or monitor the decant liquor, if you're decanting, we can give you slightly less P and ammonia in the filtrate. Those are 4 case studies. Again, they were delivered very, very quickly in days. In fact, there's another one that could have gone on there, and that's Aberfeldy. So while you guys were all up in COP, talking bullshit, talking about CO2 reduction, promising this, pledging that, Scottish Water actually delivered 2 of these schemes in those 2 weeks. And a 2 or 3 day project. Shipping container on site, connected and running. So during that time, that's what they did. And again, as I said, they've accepted the fact that we need to innovate in how we procure and how we put these systems in. Again, either of these options, it comes in a skid, a container, or in a mobile unit. We can tailor make it for you guys if you need it, or to fit into a specific footprint. However, by offering off-the-shelf packaged plant, it's very simple, very quick, very cheap, and very cost-effective in both cost and CO2. And that's that again, I keep going back to Scottish Water, you're going to be sick of this. They accepted a long time ago that they're going to have to think out of the box in the technology and innovation that they put in, not only innovation to give them different results, but also how they procure and buy and install this. They're never going to get there with the traditional design and build. And it's working well. We've got another 4 orders in just this afternoon for packaged plant. They're really moving forward to it. They're leaving the rest of the UK behind, quite frankly. Again, I'll just cover this quickly. Phosphorus removal. The flavour of the month is we're just sticking ferric dosing on site. It's a sticking plaster. So packaged plant, ferric dosing comes in packaged plant. There's quite a few that make it. They stick it on site. But what does it do? It gives you thinner and more sludge. So what they're going to do, increase tankers? No, not the way forward, but they are doing. Well, we've got a solution for that. We can put SLG packaged plant in with it. Very cost effective to deal with the excess sludge that you're producing. And we can thicken it up to 10% and still pump it. That's the mobile version. It can turn up on site, be connected in 10-15 minutes with the services there. It tows behind a pickup or a suitable size motor. And again, there are a number of these operational in Anglia and Wessex. Scottish, tow it on site, 15 minutes, it's fully operational and running. And then if you want, you can take it onto the next site. So if you've got 2 or 3 sites in a geographical area, maybe with 5 tankers, 10 tankers, 2 tankers, this can be towed around, thickened on each site, job done. Absolutely perfect for Narada, on your package plant. Okay. Skid, again, it comes on a skid. Whether it's a new site or you're ripping out the old equipment, it's in and out. It's very, very quick. Shipping container, you can have it any colour you want. What colour do you want it? Scottish Water want it green. You know, you can have it yellow with blue dots on if you want. Again, package plant, off the shelf, on site, connected, operational within days. I'll let you cover that, Matt, if you want. The last little bit, very quickly. How long have we got left? 1 minute. We can do it. For you too. Okay, thank you. Yeah, so some of the benefits are there. The increase in the sludge dryness is the main thing that we've been looking at. The improvement in the filtrate quality. From out of the 10 UK water companies, we've got results back from 7 or 8 of those, which are showing 97, 98% solids capture. So you get back to the heads of the works, it's really efficient capture rate. The viscosity of the sludge and the change of that, again, we've got evidence from 3 or 4 of the English water companies where they are tankering well in excess of 6% sludge using the SLGF technology. And we've got one other thing that I wanted to touch on. We have an R&D program where we've proved in our own facilities in the south of France, in Aix-Provence, that we think we can benefit SLG, where we put the solids liquid gas on a loop on an AD plant. And if any of the water companies want to talk to us about working in partnership with that, if they come to see myself or Andy or Sarah Dubois, who's one of our colleagues on the booth, we'd be more than interested in talking to one of the water companies about seeing if our theory actually works on an AD plant. I'll skip over that one. And that's our contact details, Andy, myself, and Vicky's here, Sarah's over. Nice to see a couple of colleagues across from France, actually. It's the first time they've been able to come here for 2 years, and they've just flown in this morning, so welcome. And that's it. Okay.
Thank you, Matthew, and thank you, Andrew, and I appreciate it that you're promoting our great Narada technology, of course, so much appreciated here.
You're welcome.
Bobby Robson said, the first 90 minutes are the most important. And resource recovery is in the first 90 minutes, of course. So again, thank you for this great story, case studies. You guys have a stand, so if anybody wants to come and have questions, they can come to the stand, of course, but maybe they have some questions from the audience right now.
Hi there, Karen Georges from Isle. So you mentioned about the carbon savings. Are these primarily because of the transportation savings, or are there also, I assume, operational savings and maybe fugitive emission savings? Have you looked at those?
We've not looked at the emission savings in detail. Operational savings, yeah. We have also seen a reduction in polymer usage and an increase in the dry solids itself, which is obviously taking down the operational savings associated with the tankers. But when we're supplying the package plant, the carbon savings associated with that huge civil infrastructure that's usually required for the traditional sludge pad, sludge building is incredible. I think that's probably the biggest operational saving. I mean, some of the tanker, we're saving just on one Thames water site, 30 tanker movements a week from one site. And if you think of the CO2 associated just with those journeys, it's incredible.
We've got similar case studies for Scottish Water as well on 2 or 3 sites where it shows specifically how many tons of CO2. And if you want to talk to me about Dalston and Jamie's work, it says there in black and white on his case study, it's frightening, the amount of CO2 that the tankers produce. Example, 8 miles to the gallon, 50-mile round trip, 76 kilos of CO2. And I'm generous there at 8 miles to the gallon. Sorry.
Any other questions? I see another one there. So these two, and then we move to the next one.
Hi there, Tim Baldock, Southern Water. Just a quick question. Are all of the case studies where you've installed the SLG and the flow set unit, or
yes.
Are you in a position where you can install the SLG unit up front of an existing thickening or dewatering plant?
Well, it's a good question. All the UK installations that we have are SLG and F. So it's the SLG and the thickening unit. Not strangely, but if we go to America, where we've got a large organisation there, it's the SLG in front of existing thickening or dewatering technologies. So we inject the air and we use existing assets there. So we've not done that in the UK. We saw the main market for us here was the thickening.
Yeah.
But just because of the size of the sites and the number of smaller sites, but yes, that's a very big part of the business for us in the US.
Okay.
Did you say you were from Southern?
Yeah.
If you talk to
Mammoth.
She works for me, that's fine.
All right, sorry, okay, and Richard Ridgway.
Yeah.
In fact, I've just recognised you now.
Okay, we had one more question over here.
Thank you. Yadira from Cranfield University. I guess just 2 points in one, really. Can you expand a little bit on your energy consumption for the process, and also in terms of how process efficiency may vary depending on sludge properties? You talked in particular about entrapped water, and EPS, for instance, will massively impact how that is removed. So,
okay. The power consumption of the flow set unit itself is 0.37 kilowatts drive on it. It's a tiny, tiny drive. So the ancillary equipment is exactly the same that you'd see for conventional thickening, with the exception that we have a blower for the air. So everything else is the same. We tend to use liquid polymer. Polymer doses range from about 2 to 5 kilograms per ton active. And when it comes to sludge consistency, the process of adding the air seems to be a leveler, because we've got installations now on all different sludge types. As I said at the beginning, we've got them on co-settled, mixed, humus sludge, pedo sludge, and we've not found a sludge type yet where we can't get a minimum of 6%. So it doesn't seem to matter what the variation is. That magic of floating the sludge seems to enable us to thicken. I hope I answered the question.
Okay, so thank you guys. Although you are from Ajax, I still give you an applause.
Thank you.
So I would like to introduce the final speaker of this first half, which is, I hope I pronounce it right, Pooja Doshi. So I would like to invite Pooja. Am I pronouncing it correctly? Okay. And Pooja is going to talk about sludge biosolid management and changing the perception of the problem. So the floor is all yours, Pooja.
Yeah, excuse me. So I think this is better. So my presentation is going to be about changing the perception on sludge management, and also basically putting sludge management into a wider perspective, and touching realms of institutional and governance and regulatory aspects. So, yes, so today I'm going to do two things with you. The first one is we're going to build a temple. So this is the construction on where we base basically sludge management. So we have underlying principles, the fundament of the temple. Based on that fundament, we have our supporting actions, which are the technical aspects and institutional aspects. And the roof they support basically the roof, which are our overarching concepts which touch aspects of sustainability and circular economy. And we also want to talk about, or I also want to talk about the barriers and the difficulties of actually achieving the change. Yes, so basically sludge plays a minor role in water and wastewater management systems. And so it's regarded to be the very end in the wastewater treatment process. And in other words, sludge is always treated as the last wagon. And we want to pursue a paradigm change and propose that sludge should be considered as the locomotive or the engine in order to choose the most appropriate choices in technology when it comes to the final reuse options. So yeah, for the following presentation, I really want you to take this picture as the main aspect and then build the rest on this. So, yes, so the fundamental principles or the overarching concepts of major interest are the laws of thermodynamics, the sustainability, and the circular economy concept. So all human-operated transformations are not perfect or fully reversible, and therefore subject to the three laws of thermodynamics, in particular the second one, according to which the entropy, which is a measure of the disorder in an isolated system, constantly increases, thus meaning that all human processes involve an energy state lower or worse than before. So basically, if you want to restate or achieve the original state, we need to put in more energy. Sludge management systems should be environmentally bearable, economically viable, and socially acceptable. So consumption of renewable resources should not exceed nature's ability for replenishment. Further, sustainability must be seen from a relative and not absolute point of view, because it strictly depends on how the boundaries are set, which should include all the operations of the entire system, and not just a part of it. In general terms, circular economy is defined as an economic system designed to regenerate itself. This conceptual definition is often and erroneously represented by a fully closed circle without considering that each cycle is inevitably characterized by some losses. For example, a waste that needs to be replaced by a new resource. The challenge is to reduce the amount of losses and the consequential need for new resources, thus quantitatively re-establishing the overall mass energy balance, also considering that the dynamics of the recycle flows are substantially different from those of acquiring new resources and or producing new wastes. So we have the circle on the right-hand side, which is an open circle, because you have to push in new resources and you will have losses. At the same time, you also have an octagon or a polygon. So basically, the idea is it's a, yeah, you could say it's a philosophical concept in a way that the full circle can never be achieved, but it can only be approached because it's limited by the physical or by the physical processes, which was depicted by the law of thermodynamics. So each process or each operation is sort of represented by a side, by a line. So it's a linear process. But the more operations you have, the more processes you have, you can sort of approach the circle in terms of achieving a mass-energy balance. So now I'm going to talk to you about the fundament of our temple. These are the boundary conditions, and they're depicted by dualistic terms. So the first one is the problem and solution. So basically, sludge is the solution of the wastewater treatment. It's what we get out of it, and yet it causes another problem because we have to get rid of the sludge. So we create a new problem. And this is basically a cycle. So the idea is basically not to view sludge as a problem or as an ongoing problem, but rather to change the perception and view sludge as being the actual solution. I would like to introduce you the concept of past and future. So in our construction, past and future is not just considered as a time unit in the sense of a progressive development. So basically, we have come quite far regarding the fact that in the Middle Ages, we didn't have wastewater treatment, and we had sort of stinking cities. And the 19th century basically offered a solution to this. And we are in the state of progressive development. At the same time, we also have a simultaneousness. So we have the existence of both states of development. So on one hand, we have very technically advanced systems, especially in the wastewater treatment sector. But at the same time, a lot of places in this world don't have any wastewater treatment. And considering the fact that about 70 to 90% of the water worldwide is not treated, this leaves, you could say, a lot of space for opportunity. The next one is disposal waste and recovery or production. Product. So this is also, again, changing the perception. Do we see sludge as a product or just as waste? And do we consider sludge to be recovered, or do we just dispose it off? So there is an ambiguity in this. And if it's a product, we have two opportunities. We can maximize the material recycling, and we can also maximize energy recovering. Yes, so sludge management basically is also a very site-specific or contextual thing. So depending where we are, we have different areas. We have rural, peri-urban, and urban areas. And we also have formal and informal settlements, for example, slums in many parts of the world. We have also very specific circumstances, such as climate conditions, soil quality, and the level of groundwater tables, which also play a very important role in wastewater treatment. And of course, we have economical, political, and cultural priorities which differ, and also the availability of technologies, some of which are very expensive and only available for a few, determine the actual choice that we make. To effectively implement a sustainable sludge management, technical actions are mainly addressed to maximize recoveries and useful materials and energy. Regarding the recovery of materials, the nutrient content of sludge is of high value, so utilization in agriculture, directly or via composting is likely to remain the major option, especially where sufficient land for spreading is available and sludge is less contaminated by toxic compounds. Phosphorus can be recovered through anaerobic digestion or from incinerated ash, while nitrogen can be recovered mostly from sludge treatment reject waters. So basically, there's no direct journey to recovery. We need to make sort of jumps, or we have certainly hubs. So the first hub is the reduction of nuisances. So the reduction of nuisances, thus improving the sludge quality, is strictly linked to that of sludge stability. Simultaneously, most of the stabilization digestion methods are also reduce the amount of sludge by degrading part of volatile suspended solids. Generally, the sludge is usually stabilized by physicochemical or biological processes. From an energy point of view, the optimal stabilization method is the anaerobic digestion, as it allows the energy recovery by transforming organic matter into biogas. The second hub is the reduction of volume. The reduction of volume is a pillar for the development of sustainable sludge management systems. However, it must be clear that the goal should not be pushing towards the production of an absolute minimum, but instead making sludge amount compatible with its final destination and the best overall energy mass balance. To this end, in addition to the adoption of appropriate technologies within the wastewater treatment stage, thickening and dewatering are the necessary steps within the sludge treatment route to more consistently improve sludge solid concentration. So with the reduction of nuisances, we basically focus on sludge quality, and we want to make sure that, we want to ensure that basically no harmful substances shall enter the wastewater treatment plants. Yes, so for recovery maximization, we have, as I already mentioned, two options. We recover the matter, the material, and the energy. So use in agriculture is the main option in case of less contaminated sludge and land availability. And energy recovery is basically, ranges from anaerobic digestion to thermal processes, the latter also allowing for volume reduction and pathogens or organic compounds destruction. So now we move to the governance aspects. So regulation on sludge cover a range of scales from national to regional and local ones, and fall not only under water and sanitation sectors, but also under health, agriculture, planning, and building sectors. Basically here we have a horizontal axis that touches different sectors of law, and also a vertical axis that basically touches, as I mentioned, from the national level to the very local level. Regarding the regulatory aspects, it appears that most of the gaps often found in many countries can be addressed to the following points: non-compliance with existing legislation, lack of capacity and resource to meet the implementation deficit, weak institutions and lack of political will for sanitation, thus not allowing to enforce and follow up existing legislation, outdated legislation and lack of harmonization of laws, prevailing perception of human excreta as waste and the lack of incentives for reuse in the existing legislation, political interference which can become a problem when decision makers, politicians and civil servants try to change the rules of the game after they have been set. The key to solve the compliance dilemma should consist in creating a clear division of roles and powers, especially at the municipal and regional levels, between the politically elected members and the municipal employees who are in charge of the implementation. On a more specific level of regulation, standardization plays a very important role. Here, we need to recognize that standardization complements regulation and also the guidelines of good practice, because well-defined procedures allow legal requirements to be fulfilled in a correct and uniform manner, thus allowing results obtained under different conditions to be reliably compared and therefore build stakeholder and public confidence. So now I would like to move to the barriers or the accessing steps to our temple. Basically, we have three major barriers: exogenous factors that are related to socioeconomic aspects, especially the access to public systems, where wastewater treatments are part of public systems; endogenous factors, which are mainly culturally immanent factors, such as certain taboos regarding waste; and also institutional factors, which is basically the failure of implementation of existing law and enforcement of law. Pricing mechanisms can be a barrier, but they can also be a remedy to accessing public systems. So in a way, pricing does two things. It is a revenue-raising instrument, and it covers basically operation and maintenance cost and ensures long-term investment. And if you remember the sustainability concept, economic viability is one of the major aspects. So we need to ensure that costs are basically met. And pricing can also help fine-tuning social aspects. So here, basically, I talk about households who don't have the opportunity to access wastewater systems. So here you can incentivize them by having very low tariff structures, and the more and higher income households would pay a different tariff. So this is called an increasing block tariff systems, which is basically which was introduced by the World Bank in the 1970s and implemented in many African and Asian countries. All right, okay. So, compliance gaps can be explained by legal pluralism. Now, I won't go too deep into this matter. You can maybe read the blogs if you can. So, legal pluralism basically describes law as not being a monolithic concept, but law, in fact, is often multi-layered, and there's an overlap. And that basically explains compliance gaps or behavioral gaps, why existing law is not implemented correctly. Yes, if it comes to changing the legal system or the institutional settings, there are different aspects of institutional change. Patent dependency is basically sticking to what has been traditionally there. Institutional bricolage would mean to mix basically new and old elements. And institutional syncretism, which we propose, would basically mean to interweave existing aspects with new aspects, which has been successfully done, for example, by the German government with the Circular Economy Act, the Kreislaufwirtschaftsgesetz, which includes circular economic thinking and resource recovery in its legal setting. Just very briefly, there are institutional dynamics. So we have the rules of the games, and we have the game of the rules, and a certain social embeddedness of rules and regulation is important, so we overcome the compliance gaps. Conclusions. So, excuse me. So basically, the first and foremost aspect is to limit toxic compounds entering the wastewater system. it's also important to, I don't know how much time do I have?
2 more minutes for you.
2 more minutes for me, okay, excuse me. Okay, so excuse me, let me just start the last part again. So in our new perception, sludge should be considered as the locomotive or the engine in order to determine the choice of technologies. So from a technical point of view, a sludge management system should assess management routes capable of maximizing recycle recovery benefits, use ecologically and economically feasible methods to reduce sludge quantity and improve sludge quality through stabilization and digestion processes, use ecologically and economically feasible methods to reduce volume to be handled through thickening dewatering processes at the appropriate level, not more and no less, develop operational systems appropriate to local and site-specific circumstances. From the governance point of view, a sludge management system should develop realistic and enforceable regulation adapted to the local context, including clear rules for penalties and sanctions, define standardized characterization procedures and guidelines of good practices, involve approaches tied to specific local economic, political, and cultural priorities and availability of tools, issue multi-layered legal norms and be subject to negotiation, understand barriers to find appropriate solutions, including the application of adequate pricing mechanisms, and setting up an institutional system capable of promoting sustainability and circular economy through an institutional process capable to interweave old and new, traditional and modern, and informal and formal elements. Thank you very much.
Thank you, Pooja. Thank you very much. Sorry I had to be so strict in timing, but soccer players know how important halftime is, and we are approaching halftime. So I would like to see if there's any questions before we go to the break.
Karen Dodgers from IR again. So you mentioned informal settlements, and clearly providing a clean and safe environment is of paramount importance there. With the 3 barriers that you mentioned, I imagine that they apply to informal settlements pretty much. But do you have any examples, or do you know of anywhere in an informal settlement where wastewater and sludge management has been done to kind of benefit those informal settlements?
Well, that's a very good question. Honestly, I don't know of any place so far where this has been done, and actually it's time that we sort of set also our focus on that, and probably also see informal settlements as sort of a future market in a way, because considering the fact that many slums in the world, or like in major cities, they are established since 40, 50, 60 years, so they're not just a fleeting thing. I mean, they are there, yeah.
Any other questions? Okay, well, thanks for your attendance, and we are going to restart exactly at 3:30 because I believe it's a virtual presentation that we have. So I would kindly ask you to be back exactly at 3:30 if you can. Thank you very much. Welcome back, everybody. A few people are a bit late. So I see a couple of yellow cards coming on. But we're going to start anyway. We now have a virtual presentation, which we're going to start. But again, after the virtual presentation, which is called Waste is Only a Resource in the Wrong Place, by Michael Reed. During and after the presentation, there's time for questions, of course. So please note them down. And at the end of the virtual presentation, we can still ask them via this microphone. So please, I'll give the word virtually to Michael Reed. Michael, it's up to you.
Thank you. My name is Michael Reed from CCM Technologies. Before I tell you more about CCM Technologies, a little bit of background, taking you out into the field, literally the field of chemical fertilizer. And in the next slide, how do I make that happen? It seems to have stuck at the first one. My apologies. Can anyone give me some steer on how to make that work? It might be a no. My apologies for this. I can give the talk entirely.
Michael, I just have a great tip for you. Can you try the space bar or the arrow keys?
Spacebar is not doing it, and the arrow keys are also not doing it, although they normally
try
would.
any key. Maybe you want to restart or something like that. Maybe that's a good idea.
I think I might. But forgive me, everybody.
Okay.
Let's have another go at this. So that's the PowerPoint presentation there. And from the beginning, there we go. Does this work? Yes, it does. My apologies for that. So, The field of agricultural fertilizer is a wonderful success story. In the last 70 years, the world has quadrupled the food production that it's capable of, largely due to the application of chemical fertilizer. But there's a huge but in there. And the but is that this fertilizer use is linear. And I'll just run you through how it goes. What you do is you dig minerals, phosphorus and potassium out of the ground. You then take the methane out of the ground in the form of natural gas. And then you take that and use it to capture nitrogen to produce the nitrogen for the fertilizer. You put it all together and you have an NPK fertilizer. It's bog standard agricultural fertilizer, and your plants grow bigger and produce heavier crops. This is a good thing, except that what happens then is that some of that N goes up into the air as it volatilizes. As any agronomist will tell you, only half of the nitrogen that you put on the ground actually gets used by the plants. The rest of it gets washed down into the aquifer or off. So does the P and the K. And the plant uses what's left over. And it uses that to produce biomass and food. The food is then processed, creating more waste, and what isn't waste is then eaten by human beings. And once it's been eaten by human beings, it is up to the wastewater industry to deal with what is left. That is usually put to land as anaerobic digestate, which is seems like a bit of a circular thing, but what you can do with that is limited. You still get the N volatilizing, even more so. The P and the K also wash off and in. So, and it costs a lot to do. So there's a problem there on that side of it. How can we make it circular, properly circular, so that you get proper fertilizers in at the front end that have come from the back end?
Are you there, Michael?
But they're also held in other places, as we'll see. This gives you new routes for returning resources to the economy. Conventional fertilizer analogues with high organic content is what comes out of this process. What we do is we basically create a pelleted product. Pelleting digested is nothing new, but what we have now is a standardized NPK fertilizer that is stable, that won't volatilize, that washes off and in much less, and has quite a high organic content, up to 50%. It's less polluting. It has lower nutrient application rates. Why? Because it is a slow release fertilizer. You don't just get a big bang of everything that's pumped onto the field. It releases it slowly so that the plants get it when they need it. And this reduces waste there. It enhances the soil health. The bugs in the soil love this stuff. For obvious reasons, it's what they've been eating for millennia. And it increases the carbon in the soil, which has been reducing for many, many years. It also increases the micronutrients in the soil. Research has shown that a typical apple bought in 1960 had twice the number of micronutrients in it than an apple bought today. This is due to soils degrading. So what's the market? What's the potential? In the UK, in 2018, we used 3.5 million tons of nitrogen, 1.8 million tons of phosphorus, 1.8 million tons of potassium. It's a lot of material. But interestingly, in recovery potential, human waste, well, you've got half of it already there, 1.8 million tons. Food waste, 2.5 million tons. Agricultural waste, 4.2 million tons. You start to see the tapering effect of the production of food and where all the nutrients go from those numbers. And if you look at the P&K, 2 and 3% million tons respectively. And if you're looking carefully, you'll notice that there is more available in waste than there is that we need. Why is this? Well, interestingly, a lot of our human and animal feed comes from overseas. We could be exporting it back if we could stabilize that. And this is the point. The big resource availability is anaerobic digestion. And if you can stabilize that, we have a market which we could be selling to of 12 million tons annually. That's just the UK. Currently sent to land with all the restrictions on that activity, and there's a big challenge and competition between the various producers of digestate cake, as you know. What could they do? Well, they could be a big earner. This makes money. It isn't a way of solving a problem. It's a way of making money. It does solve a problem, but it is cash positive. Carbon sequestration, making money out of getting carbon out of the air is something that is going to be seen increasingly. And avoidance, all of that methane that you don't have to burn to make fertilizer. This is one of the installations we've got at Severn Trent's Minworth plant. This big shiny stainless steel plant is the culmination of a decade of work. It took 7 years to create a way of producing a stable and commercially viable product out of these waste streams. It's not easy. And we've been focusing not just on wastewater, but food waste and agricultural slurries for obvious reasons. And we've had to solve a lot of problems, and solving those problems is difficult. But the upside is that we're solving problems that nobody's solved before, so we can get patents granted on it. So we have this technology which we're rolling out. This is our little plant in Swindon that we demonstrate on. This is been operational for the last 2.5 years, and we can actually use it to produce customized products at 20 tons per day. We can mix it, we can react it, and we can automate the system. It can run with the lights out. How do we do it? We take those solids and the acquired nutrients, and we combine them with the big problem chemical, CO2. We stabilize it. That's the key stabilizing part. There are other stabilizing ingredients and balancing nutrients, and we create an analog of an organic fertilizer. So what we have here is another case study. PepsiCo Walker's Crisps. And it's perfect circular economy. So you pick potatoes, you peel them, you make crisps, you anaerobic digest the peel, you take that digestate, make fertilizer, ship the fertilizer to the field, put it on the field, grow potatoes, peel them, etc. And we've been testing for 7 years now on various crops. And we found initially that it was the same. We could do the same as we could with the chemical fertilizers. And over the years, we have been making that more stable, more and more stable, and improving the slow release quality of product. So we're able to put less on the field and get the same crops, but we're also doing all of those other things. We're looking at carbon in 3 ways. We are basically capturing carbon in the actual process. That is our main reactant there. That goes out into the field and is on the field in a solid form. We are storing carbon in the ground. That comes from our digestate material that's been stabilized in such a way that it stays in the ground for a significant period of time. And we're avoiding huge amounts of carbon being pulled out of the ground in the form of gas and turned into nitrates for fertilizer. So this is the 3-fold way that carbon is beneficially impacted. So what does that mean? That means if we only put 5 of these units, and there are thousands of potential sites, so 50 of these units out in the field, we would be removing 1.75 million tons of CO2 per annum. That's just in this country and just a small number of units. Putting that in context, it's the equivalent of taking 375,000 oil-burning cars off the road. Electric cars don't count. We're very proud to be part of the 1,000 technological solutions that are in the Solar Impulse Foundation. I don't know if you've been following the story on COP over the last couple of weeks. It's been 2 main themes. One is governments promising to reduce carbon emissions, making pledges to reduce carbon emissions, and to put legislation in place to reduce carbon emissions. Protesters demanding that carbon emissions are reduced. It would be a different type of COP if instead the stories were we are focusing on the solutions to produce those carbon reductions. That is our main policy focus, making them work, making them financially viable. And the protesters saying, we want you to be putting those solutions in place faster. It's a different picture and a different aspect, and I believe a much more positive one. Those solutions are out there. They just need the support to put them faster into the field. But don't get me wrong, ours is going into the field now, and it will be continuing to grow as time goes on. We got part of the 39 Ways to Save the Planet, a BBC series recently. And a quote from that is, can we have the crops without the carbon? Yes, we can. We take the waste streams and turn them into fertilizer that emits 90% less CO2 in production. That's just one of the carbon corners that we saw earlier. So that's CCM Technologies. We have a financially viable system without any subsidies or anything else. It will make money because we're producing a high value output. We're replacing an unsustainable product, and we are making a difference already, and we're growing quite fast. And that's why we're saying that waste is only place, as Mahatma Gandhi said. And that's it.
Thank you, Michael. Thank you, Michael, for a great presentation. Any questions? Here.
Hello, Sarah Jane Westlake from Atkins. What regulatory framework are you recycling the fertiliser under? Is it, have you got end of waste, or are you doing it under the fertiliser regs? Or is it sludge use and agriculture regulations? How are you recycling it?
That is a massively important question. So the answer is all three. There are some streams which we can put straight through fertilizer regs because fundamentally none of those streams are waste. There are some being done through permitting, and we are working with the EA on how the remainder of the potential is properly put to end of waste. That is an ongoing process. Basically, if you go to the EA with something that's never been done before, that takes a little while to sort through. But that is the $100 million question. But the ones which we are doing are being put through those other two routes.
Any other questions? There's one over there.
Hi, Michael. It's Dave Tompkins from Aqua Enviro. And apologies for putting you on the spot slightly, and feel free to take a hospital pass on this question. I wonder if you could say anything about how the ammonia gets out of the effluent and into your process. Does it have to be kind of a clean ammonia stream, or can you put the effluent itself through your manufacturing process?
That's a very good question, and it's one for which we have half the answer in production and the other half of the answer in development. So the production half is that if you take digestate cake, everybody thinks it's a solid. Of course, anybody who looks at it and does some analysis finds that it's somewhere between 21 and 26% solids. The rest is water. And of course, dissolved in that water is ammonia. So the first thing we do is we make sure we stabilize that ammonia. So that's the first bit that is actually in place, and that's that bit. The other bit is the ammonia that is in the liquor stream. Prior to producing cake, I'm sorry to teach my grandmother to suck eggs. Everybody in the room probably knows this much better than I. You are basically squeezing the sludge that comes out of the digester, and there's a liquor stream which also is rich in ammonia. That is something which we are working on at the moment. We have pilots that we are working with Yorkshire Water. That also takes phosphorus out as well as ammonia, and so that's the second part of the answer to the question. I hope that helps. It's something very much front and center of of what we do, is how that ammonia is stabilized and included in this. And we've recently done trials that shows that if you take a digestate cake and put it on the field, one warm day at 25 degrees centigrade gets rid of 33% of it. Just goes straight into the air. Which is a bit of a waste, really. So what we're doing is we are tying that up and making sure it is available to plants.
We have time for one more question, if there's any. So thank you, Michael, again for your presentation.
Thank you.
So I think a good presentation. Waste is only a resource in the wrong place. And we are here actually at a very nice place. Not maybe the best place to play soccer or football, because I understand that Newcastle United is not doing very well in the Premier League. They did in the past. So I have a pop question for you. When was the first soccer match played here on this ground? Anybody? Correct. Immediately. So imagine, they've been playing soccer here for, let's say, 130, 140 years. Amazing. Okay, let's move to the next presentation, reinventing the end of waste. So I give the word to David Tompkinson from Aqua Enviro. So, David, the floor is yours.
Thank you very much indeed. I'll just say I'm a big fan of organomineral fertilizers. Although this presentation wasn't designed to cover them specifically, a lot of the remarks are relevant to OMFs. You will notice a couple of things as we get into this. Firstly, I've lost my co-author. So Nina Sweet is not alongside me here. As part of the conference organizing team, I have to be flexible about where my presentation appears and what topic exactly it covers. So it's moved around the program several times, and it wasn't actually clear that I would have to give a presentation until about 5 days ago. So that wasn't enough to run anything past Nina Sweet. So that the benefit for you, if there is one, is that all of these remarks are mine. So there's no one else to blame other than me, and there's no one else to ask or answer questions other than me. So that may or may not be a good thing. You know who AquaEnviro are. I'm not going to spend any time on that slide. Just to highlight, we're not just a conference organizing team. We are a wastewater and bioresources consultancy, and we're part of the Suez group of companies, and will remain so, but we act still independently as much as we can. So what I'm going to go through today, this is my kind of introductory slide, the context, where we are, and why I want to talk about what I'm talking about. Exploring some of the current regulatory frameworks as they pertain to digestates. And this is not sludge digestates specifically, although I will loop in some thoughts and comments on sludge digestates. This is more farm and food digestates. And then give you some ideas, float some ideas for options for change, how we might do it differently. So where there are some issues that we might all agree on as common problems, and some potential solutions to those problems. I couldn't stand here and say, here is the answer, this is how we can fix it. I'm just going to float some thoughts past you. We'll have an opportunity to discuss them in the break afterwards, or during subsequent meetings, and possibly during tomorrow afternoon's panel discussion. And then I'll bring that together with a few conclusions at the end. So the context of the presentation, when I originally submitted the abstract for this presentation, I was anticipating that come now there would have been significant advances in the redevelopment of the AD Quality Protocol, and that we would have seen at least a draft for consultation of new UK fertiliser regulations, which would be more or less based on the EU fertilising product regulations, probably, in my view. Both of those are vehicles for end of waste for certain materials under certain conditions, and would have given me a nice kind of leaping off point for the rest of the content of this presentation. Unfortunately, none of those have really gone anywhere in the past 6 months. The funding for the ADQP has been agreed, but nothing's really happened. The new fertiliser regulations haven't been put out for consultation. I'm assuming DEFRA is still scratching their heads, probably slightly hung up on the fact the European version includes end of waste for digestates and excludes most sewage sludges and derivatives. So we have opportunities to do things differently now, and some of those thoughts I'll amplify over the next few slides. So rather than those vehicles as kind of stepping off points, I'm going to use this, which is a project for Renewable Energy Assurance Limited. You may know them in the guise of the Biofertilizer Certification Scheme and the Compost Certification Scheme, or the PAS 110 and the PAS 100 schemes for short. The members of those schemes pay into a research pot, and there is a process by which they tender opportunities periodically, and I'm part of a consortium that's just finishing a project, the second Research Hub project, which has informed a lot of the thoughts I'm going to share with you now. The official title of that project there is on the screen, but that massively belies what we've actually done in the project. So one of the three of the partners has gathered together data on UK digestates, their characteristics as far as available. But actually, I spent most of the project looking at valorization options and issues, and trying to kind of map out a route to market through the existing regulatory frameworks, and highlight some deficiencies in those regulatory frameworks, and some suggestions on a policy, regulatory, and industry level for how they might be changed. At the moment, we've kind of got something that works for where we were 30 years ago. We haven't really got something that's fit for purpose for the future, particularly when you start thinking of kind of circular economy concepts. The regulations are really, really straining at the seams. So we are focusing on farm and food or agricultural and commercial digestates for 2 reasons. The biofertilizer certification scheme mostly has farm and food digestant operators on its books, so it's only interested in those. Plus, we also expect that to be where the growth in the industry comes over the next few years on the back of compulsory food waste collections being introduced from 2023 onwards, so that's the commercial AD. And then possibly the focus on low carbon farming, the desire to get more manures and slurries into AD and to get the renewable energy benefits. So we're expecting to see some growth there and some opportunities. We will all know that digestates from both the food and farm sectors are going to land as most sewage sludges go to land. That's great. It's a fantastic biofertilizer if you can get it to land at the right time, under the right circumstances. And that is a common issue across the sectors currently. So one of the main drivers behind innovation, I'll call it innovation, really it's not innovation, but it's kind of the development of ideas for addressing regional nutrient surpluses. Nothing fundamentally has changed very much in technology terms for at least a decade in this space. And having been back through it over the past few months and still going through it for another client, the lack of innovation is slightly astonishing. But it could well be a simple reflection. There has been no market pull or requirement or push for there to be innovation in this space. So where we are seeing things being tried a little bit differently, it is elsewhere in Northern Europe where there are livestock-induced regional nutrient excesses. So the game in town has been to get the nutrients from where they're in excess to where they are required. And in Flanders, the Netherlands and Denmark, parts of Western Germany, parts of Italy and Catalonia, livestock manures and slurries are moving hundreds of kilometers to land. So land is still the cheapest direct route, but it's costing 20 to 25 euros a ton to get livestock manures to land in some parts of Europe. Some AD operators can charge a gate fee for livestock manures in Europe. So it kind of, when you look at the problem through that lens, suddenly it's very different from our market. But actually, in my view, that is also the direction of travel in our market. I'll mention the farming rules for water just once and leave them. We'll come back to them tomorrow. If we're looking at kind of holistic nutrient movements, benefits, that is where the direction of travel has been. There are plenty of lessons to be learned there. So a typical approach in Europe: dewater your slurries, export, compost and export the fiber fraction if you need to, and then put the liquors through nitrification, denitrification. Great, you've solved the regional nitrogen problem. It's completely contradictory to any kind of circular economy principles. You've lost the agronomic value of the nitrogen, but you are compliant then with the requirement to manage the nitrogen load regionally. Where that's led to is farm-specific nutrient quotas, centralized nutrient planning in places like Denmark. Annually, you have to log your nutrient management plan with the central authority, and they will check that you've done that. Fertilizer suppliers also have to register their supplies with the same agency so that all the dots can be joined up. In Flanders in the Netherlands, there is a requirement to process manures. If you've got more than can be applied to land within your holding, you have to process it. And that means either getting it out to another market whole or through some kind of, I'll call it genuine processing, some kind of nutrient removal or recovery process. So it's kind of, if you step back from where we are and you look over the channel of what's been happening, it's kind of, oh, interesting. Is this where the farming rules for water might take us? Possibly. And there's a lot of really, really pointed language in some of the DEFRA and agency communications around farming, particularly. I know the water industry feels a little bit persecuted, but actually the agency is coming for farmers if DEFRA will let them. That's the language. It's kind of, yeah, we're moving in an interesting direction. For me as a consultant, fantastic, lots of innovation opportunities, lots of things we need to try and show don't work or do work, and lots of issues with the regulations. So the current regulatory frameworks, and you will have seen a version of this slide before, and I just wanted to use it to highlight the problems we've got. So these, depending on the feedstocks you start with, what comes out of your digester may or may not be a waste, and it may or may not be a waste depending on whether you're north or south of the border between Scotland and England. So crop byproducts, for example, are something the Environment Agency are quite comfortable with. That's not a waste when you digest it, so your digestate's not a waste, but in Scotland it is. If manures and slurries go in, thanks to the Waste Framework Directive, that is a waste management activity. Your digestates are a waste. Your digested manures are a waste, but they are not regulated when it comes to land application under the environmental permitting regulations. So they're in, they're out. Waste, so food waste, commercial food waste, domestic food waste, what comes out? Yeah, it's waste. Waste went in, waste is coming out. But you can go through the end of waste process, through ADQP or the PAS process if you're in Scotland. So yeah, they're in, but they're out, but under certain circumstances. So the end of waste positions only apply to certain very specific uses for certain digestates. This is about digestate to land. This is not about digestate to domestic consumers. This is not about digestate being concentrated and sold through gardening stores, for example. It's kind of, yeah, if you do X with Y, then you can do Z with that material. So it is demi-flexible currently. Sewage sludges, they are wastes. I'm really sorry. They're derived from wastewater, so it's kind of in the language. Wastewater turns into sewage, it's waste. That's where we are. I know it makes some people very uncomfortable, but at the moment, the use of those materials is not captured by the waste regulations. I know that's something else that's also possibly changing and is subject to some ongoing discussion. I won't get stuck up on that. So here's an example of the response from Europe, if you like. I won't call it a typical AD plant in Belgium. It is an AD plant in Belgium, in this case taking a combination of manures and domestic food waste. And those technologies won't be particularly surprising, interesting, innovative to you. You dewater, you can dry your fiber or your cake. They are then scrubbing the ammonia out from the dryer. The ammonium sulfate's going in with the liquor. Then you're acidifying in storage, which keeps the ammonium in the liquid. Then you're evaporating to make a concentrate, go through RO, and so you've got effectively water, a concentrate, and dried cake coming out of that. So if we just focus on all of those outputs, this is where we are. If I implemented that system tomorrow here, anywhere in the UK, all of those outputs are waste, including the clean water. None of the current regulatory end-of-waste frameworks we have would apply to those outputs currently. And interestingly, or slightly amazingly, because you've got manures going in the front end, thanks to the nitrates directive, anything that you do with that manure will never, ever stop it being manure. So you could make a mineral ammonium sulfate fertilizer through stripping and scrubbing, and it is now a mineral fertilizer to all intents and purposes. But thanks to the nitrates directive, it's actually still livestock manure. It's only relevant if you want to use that ammonium sulfate solution in an MVZ, as you could with any other conventional fertilizer to meet crop demand. But you can't currently because it's still classified as a manure, which slightly surprises me. Food waste and manures are both animal byproducts, so there are processing and traceability requirements for kind of ongoing compliance with the ABPR. So although end of waste itself is an issue, there's a bunch of other associated threads in this Gordian knot that we need to cut through or sort out somehow. So yeah, the waste status might not actually be the most significant problem we've got here. So I've lifted the text of the end of waste test from the DEFRA guidance. I might read some of it out to you. I think it's pretty self-evident. You've got to have a purpose for it, you've got to have a market or demand for it, and it's got to fulfill that purpose. They all seem pretty fine to me. And then this is where things start getting a little bit challenging. The use will not lead to overall adverse environmental or human health impacts. And judging that, for me, is one of the most significant problems with what we've got currently. So if you're starting with, I'll say, a relatively simple material at the front end, pick one, livestock slurry, cattle slurry, okay? I could put some boundaries around that in analytical terms, given the source and where I might want to use that. If I put sludge cake into that same space, that's suddenly a whole lot more challenging to set some kind of analytical or risk assessment boundaries around in a way that will allow us to demonstrate the quality of that material on an ongoing basis, as you would with any other product. So I'm not saying we shouldn't have a sludge standard. I'm saying it would be really challenging to address all of the hazards that are present in that material compared with the hazards that are present in other materials, which are fewer and more straightforward to characterize and limit. A question which I will leave floating, in the end-of-waste process, why would you involve the regulator at all? Because you don't have to. These bullet points, again, are lifted straight from the government guidance, and getting an opinion through the Environment Agency's Definition of Waste panel is now at the bottom of that list, after doing a self-assessment. And I don't know if whoever created that website did that deliberately, but there is no requirement for you to get a view from the agency if you are confident enough in the data that you have developed around the compliance of your material with the end-of-waste test, which was on the previous slide. If you're an individual business creating one individual new product, doing it yourself might be a sensible thing to do. For a sector to do it without the regulators' buy-in, I think might be a little bit short-sighted. But at the same time, to get their buy-in and involvement would also be massively challenging. So let's explore this question of assessing adverse impacts in a little bit more detail. So again, this has been lifted from the government website. If you've got a non-waste comparator, you compare it. Okay, that's relatively straightforward. You've got to be confident you've picked the right comparator, both in terms of storage, use, haulage, all those kind of things. And then depending on the source of your material, you may need to analyze for more things in your material than the virgin comparator. If you don't have a virgin comparator, or actually the levels of particular hazards are at higher concentrations in your material, then you will probably have to do a risk assessment of some kind. And risk assessment is where things get particularly thorny. So many of you will be familiar with the work of Steve Smith at Imperial and others in the UK market who do risk assessments for sludges on almost a kind of an annual basis. This is a report that was published last month. It was a piece of work I was involved with 2 years ago and I'd forgotten that I worked on, but the report was only published recently. And this was led by the Macaulay Institute for Scottish Government. And it's a typical project. You start by looking at the literature, what are the hazards present in this material, and you end up very quickly creating massive lists of things, and more lists of things, that you might be interested in your sludge or your material. You might not be concerned about those things, but they are there. Now, this is an issue that Keith didn't flag in his opening presentation this morning. No, he did. If you look for it, you'll find it. These days, analytical techniques are so advanced now, you will detect down to parts per trillion. That doesn't automatically mean there's a problem. It just means a hazard might be present. But because of the risk assessment process, now you've identified that it's there, you've got to show that it's not a problem. And for many of these hazards, the exposure data, the impact data, simply do not exist. So in risk assessments, you end up making a whole load of assumptions and precautions and grouping hazards together, where you've got you know the behavior of one of them, but not all of them. So you end up reading across the behaviors and making all kinds of precautionary assumptions to give yourself some hope of getting an answer. And you could not do this on a product-by-product basis with sludges at the moment. It's just not an appropriate framework to use. And these are the end results, some hazard quotients. So if it's more than one, it might warrant further investigation. If it's less than one, it won't. I won't dwell on that for time. So options for change. So I'd like to suggest we shift away from a reliance on lab testing a little bit. Let's not necessarily analyze for everything, but let's also review how we do risk assessments. One of the big challenges when I've done risk assessment is they all tend to be one hazard at a time, and the feedback from the stakeholders is, yeah, but that's not how the sensitive receptor is exposed. They're exposed to baskets of hazards at one time, and by analyzing one, you might be underplaying the risk. Okay, that's a reasonable challenge, but you need data to inform these kind of multi-hazard approaches. If you've got those data, fantastic. The tools are now available to do that kind of multi-hazard simultaneous modeling, which are way beyond my capabilities, but they do exist. Or let's think again about some of the ecotoxicological approaches. The ones we have at the moment, the Daphnia, the earthworms, they're not really ideal for these purposes, but there have been huge advances, particularly in the contam land sector with biosensors. So they're cheap, they give you a quick answer. Basically, if the green light comes on, it's fine. If it doesn't, it's not fine. We're nowhere near that as kind of a common product test for some of these materials yet, but why not? Why not aspire to develop a solution that gives you a green light for your product without you having to go through the £1,000 a sample emerging contaminant test every time you want to get something to market? So there are other ways of approaching these problems, and there's some suggestions here. So, regulatory harmonization. I already mentioned this issue. Will your fertilizer be used in NVZ? If it's manure-derived, that's a problem. If it's manure-derived or food waste-derived, then it's an animal byproducts problem. And this one, will you be making more than 1 ton a year? Because now you are invoking REACH. REACH is kind of unavoidable. I think I'll cover it. Yeah, here we go, on the next slide. And as with all the other regulatory frameworks, there are exemptions and non-exemptions and exclusions. So if you're a waste to land, you might not like the idea your materials are waste, but actually you're exempt from REACH registration. Happy days. Digestates and composts and other kind of natural materials are also exempt from REACH. So then we're into an interesting discussion. When is my digestate no longer a digestate? If I strip out ammonium sulfate, that's not digestate, is it? Well, no, but nothing anywhere in guidance or regulation says that there is a defined end point for your digestate. I would say it's definitely not digestate anymore. If you're producing more than 1 ton a year, you are now captured by REACH. You will have to submit a dossier with a load of information in it to get it registered. And at the moment, each producer needs to submit a dossier for each substance under REACH. There's nothing to stop producers collaborating to produce joint dossiers, but at the moment, this is where we're at. REACH regulation has been ported across to UK legislation. It's now managed by the HSE. But it also still points out to a lot of the European guidance because they didn't have time to cut and paste everything into the HSE format. So there is guidance on here on hazard and risk assessment, how you might do it for substances. And my key point here is if you need to collate a load of exposure data, risk data for REACH purposes, then why not make that also applicable to the end of waste purposes? Let's see some cross-linking between these regulatory instruments and some common sense applied to the types of data, how we gather it, and what we deem acceptable. So that would involve the HSE and the environmental regulators getting their heads together. And I know they collaborate already because of the REACH registration. So the last few slides. Here is a framework that has already sought to tackle some of these issues, the EU Fertilising Products Regulation, or FPR for short. It's, I think, potentially a useful framework. It does work through some of the Waste Framework Directive issues, so there are defined end-of-waste points for some of the component material categories that are used to develop the fertilisers in the product function categories, get my acronyms right. And it does in part seek to address the questions of manure, the Nitrates Directive 1, and the animal byproducts regulations. And it does include some sewage sludge derivatives currently, but it doesn't avoid REACH. So it's an interesting exercise. A lot of work has been done to kind of overcome these regulatory dead ends. And we, I would suggest, have an opportunity to reflect on that experience and recast our current regulatory frameworks in that light. So let's see some read across the various instruments and simplify the data gathering and submission processes. We won't get the EU FPR because of Brexit, but that should say the Agriculture Bill does make provision for new UK fertiliser regs. I was expecting them to have been consulted on last year, but they're already late. But do look out for them, do engage in the process of development of those. So some conclusions, and then I will just have, I think, one slide on impacts for biosolids. So we've got some lessons to learn. Current regulatory framework is frayed around the edges, and it is creating uncertainty across sectors, waste and water. And uncertainty means risk, means lack of investment, means inertia. as derivatives become more complex or are supplied to different markets, we need a much better way of characterizing and assessing risk, particularly when it comes to product standards or specifications and how we define those and how we demonstrate compliance against those. And there are some tools in the toolkit to allow us to do that. We could, I would suggest we should, recast our regulatory approaches to facilitate that kind of cross-instrument, the ABPR, NVZ, ND, WFD. Let's get some read across here and some commonality in our data requirements. And I've talked a lot about fertilizers, stuff to land, but CO2 from biogas also falls into this problem. It's a waste. If you are producing your biogas from a waste input, so if you're a crop AD operator only, happy days. That's why I think we're seeing some innovation in the crop AD space completely conflicts with renewable energy requirements where we don't want to devote land to energy crops for anaerobic digestion. So we're not going to see any growth in that sector, but we are seeing some innovation in product outputs. We are seeing CO2 from biogas upgrading from crop-only AD operators going into the food chain. If that was waste-derived CO2, no. It's a challenge. There are a bunch of traps out there. So what does it mean for biosolids, finally? I think converting sludges into products remains and will continue to be a massive regulatory challenge simply because that's where many of the hazards partition during dewatering. Nothing more nor nothing less than that. I'm not making a judgment about it. I'm a big fan of biosolids to land, but hazards end up in the sludge fraction. And we need a way of, well, we don't have to recognize it, but we need a way of getting through that kind of mental block. Because if we choose to develop an end of waste approach for sludges, we are leaving ourselves open to this continual what about from the regulators. Did you think about compound X? Where is your evidence for compound Y? And the answer is going to be no, no, no. And I'll use the language because the regulators have used the language. In their view, this is mixed waste. If I stepped out and sat on the solid waste side of the fence, the nearest analog is the mechanically reclaimed fraction of bio-waste from residual black bag waste. And they have never, the Environment Agency have never approved an end of waste position for that material. No reason they shouldn't, I'll wrap up. But that's the mental equivalence that I'm seeing happening within the regulatory community. Dewatering liquors, I think, present fewer challenges. We've already got end-of-waste precedents for struvite. The FPR in Europe does include phosphate salts and various ashes, so slightly more straightforward. So, final one. Regulatory framework needs to be recast if we're to get anywhere near this kind of circular economy principles. I think we need 3 revolutions. I think I only put 3 on. Revolution in risk assessment, a revolution in testing to demonstrate safety consistency, and a revolution in regulatory approach. None of that's impossible. Are we up for the challenge? Thank you.
Thank you, David. Any questions?
Snuck in, Keith.
Come on. Keith.
I didn't see you there, Keith. I thought this presentation could have been designed to press your buttons.
Well, because I got talking to Paul Fountain, that's why I've only just got here. But so anyway, I don't know if you saw my presentation this morning. Okay, I was being quite. We're looking at the future, but actually the future exists if you look elsewhere. I mean, we've had the US EPA regulation since '92. They very specifically made a grade of sludge called exceptional quality and set a specification for it. The problem is that we've been led by the nose by RAP and the agency into this input specification, and that all started with the compost lobby in Italy. We came through into the Compost Association. I joined them to stop it happening, but they still went for it, and we got PAS 100 and PAS 110. They're not the spec for us. We as an industry have to define the spec for our final product. And I alluded to that this morning. This is a million miles from where we are at the moment, but it's going on in the US. No one gives a blink. They make products all over the place and market them without any cross-reference to any other regulation because their regulation enables them to do it. Everything we've got is disabling. And so it just needs chucking out, and we just need, my opinion is, it's a radical one. I'm not sure we'll win the battle, but my opinion is that as an industry, we need to say, these are the metals, these are the pathogens, this is the stackability, stackable, stable and safe, and these are the total volatile organic sulfur compounds that go with our stability. This is a spec, and once we meet that spec, it's no longer waste, and we're going to take it to farmland, and we don't have to ask you. Now come and prosecute us, and why? Okay, that's my challenge.
Thank you, Keith.
I kind of would like to take a hospital pass on that for two reasons. We're going to be getting into whys and wherefores of future sludge management tomorrow afternoon. So I really want to I'm going to raise that question with the panelists tomorrow afternoon. But I will respectfully disagree with you. And for well, I could do it for many reasons, but I'll do it for one reason. Where are the stakeholders in that? So you did very nicely flag the issue with Tesco's, the BRC, and the maltsters this morning. I have had my fingers burnt on the waste side of the fence by the same group of stakeholders who switched the market off for compost and digestates in Scotland overnight because they didn't like what they were seeing. So it's all very well saying we should create a standard, insist the regulators go for it. Unless you get those stakeholders on board as well, you're not going to go anywhere.
Thank you, David. I have also a question for you. I've been over the last year involved in Caumera. Caumera is a natural biopolymer coming from the Nereda granulus. And we went to this REACH and end of waste dossiers for the last 2 or 3 years. We're almost there. And I think there's also one key component, and I would love to be in your discussion tomorrow as well. If you have a contract where you can actually sell the material to an end user, that makes your case much stronger. So that's a free tip.
Thank you for that. It's a really interesting point. It's not one I had time to cover, but the question of value for the material and demonstrating a market. Yeah. And certainly in the commercial AD space, and to a lesser extent the farm AD space, it's about getting rid of stuff. Digestate is a loss center. It's not an added value center, but nonetheless farmers like to use the material, so they're not necessarily covering the costs. They like to use it. Does that make it a viable market in the eyes of the regulator?
That's correct. I know it for Caumera because Caumera is also used as a biostimulant, but we are looking for example, for Caumera to flame retardants and to coatings, so higher value applications. Yeah. And that makes it, of course, a very good business case, and it will help you reach and you end of waste dossiers.
Yeah, that's a great tip, and I will shut up in a moment. But I focused a lot on fertilizers, as that is where the market's been driven in Northern Europe for livestock slurries and kind of farm digestates. But that's, to use somebody else's words from today, that is focusing on the problem rather than the opportunity. So the opportunity should be to go for where the characteristics in that material are that will end us up in a valorization, a value product or products of some kind, and focus on those. So we need some kind of leapfrogging of where we are at the moment. So I agree with Keith. We can and should be doing things differently. I don't exactly agree with how we might do it, but we've heard some ideas today, and we'll come back to them tomorrow. So thank you.
So thanks, David. Any other questions? We have time for one more question. Then we go to a virtual tour, actually, of Howden sewage treatment works. Malik, give the word to Alex soon. I understand I'm not very familiar with the geographics, of course, of the UK, but Howden is close by, as I understand. So I give the word to Alex.
Yeah. You have to bear with us a little bit, because usually when you go to Biosolids conference, we always go to a site tour. So you've got to believe we're in a site tour now. So you're in Northumbrian water, and our biggest site is literally 3.5 miles down the river at Howden. But because of COVID and other things, we couldn't do that. So what we're going to do instead is a presentation by Richard Murray, who's the Wastewater and Bioresources Manager for Northumbrian, to go through the evolution of Northumbrian sludge strategy, followed by a video tour of Howden, and then a question and answer session after that. So, Richard?
Okay, good afternoon. So, as Alex said, I head up the operations side of things for wastewater treatment and the bioresources for Northumbrian Water. And I usually do this as a double act with Tony Rutherford, and he's in the virtual bit. And he's been on telly twice already this week, so that's why he wanted to do the virtual bit. So, without further ado, what I want to do is try and take you through just what our story's been from a Northumbrian Water point of view. Because our strategy has gone through various different phases, some successful, some not so. And really, what I want to do is give you a good news story right up to the point where we're talking today, where farm rules for water come into play and can somewhat jeopardize some of the strategy that we've got. But we've got to be innovative in terms of how we take that a bit further. So, in terms of strategy development, prior to 1995, we didn't even have any sludge strategy. What we did was we had a few inland anaerobic digesters that didn't work particularly well. We relied heavily on landfill, and we also relied heavily on marine dumping into the North Sea, which was the best prawn fishing grounds in the North Sea, because all the trawlers used to follow it. But come 1998, that had to cease. We didn't have any coastal treatment either. Our estuarial plant at Howden, the Newcastle plant, was only a primary treatment plant at that point in time. And on Teesside, we had virtually nothing. And all of the coastal sites were direct discharges into the North Sea. So we didn't even have all of our sludge at hand at that point in time. So we needed to come up with something that was going to deal with all of the sludge and all of the future sludge going forward. So what we came up with at the time, and the likes of Martin State is in here, and he was part and parcel of how all of this pulled together for the drying phase of our strategy. We came up with the fact that we were going to dry all of our sludge. It was deemed that was the right way to go, because sludge to agriculture was in a vulnerable state at that point in time. And we wind ourselves forward again, and we find ourselves in a similar position. But the drying gave us the opportunity where we could produce a product which was going to be available to us as a fuel as well as a potential fertilizer. And what we would do is we would build one drying plant, and that would be on Teesside at our Brown Sands plant, where we had to put in extra effluent treatment to deal with the treatment that just wasn't there, and the industrial sources of effluents that were going to arrive at us as well. And to get everything there, what we were also going to do is transport it by the ship that we used to have to dispose of the sludge into the North Sea, and we even bought another ship to help us do that. Now, the inland sludges remained a little bit unchanged, but we had to start introducing some dewatering and lime stabilization processes. Now, we had to set those up at Howden and our Berkeley plants, and that was purely because the drying plant that we built could never get up to the capacity that it was ever designed for because of reliability issues. So we introduced a second location where we were processing at least half of our sludge, and that was the lime stabilized sludge. Now, we actually went through 2 plants of lime stabilized sludge at Howden, because the first one rotted to bits, and we then had to rebuild that again, and we did that quite innovatively, using Agrovert as our assistants to do that. So just to give you a bit of an idea, that's one of our dryers that you can see up there. And we had 7 of those at Brown Sands, at our RSTC, as we called it. And that was designed to process at least 70,000 dry tons, but we never quite got there. I think we managed to get 7 of the dryers run all at one time at one period, but not for very long. So it was a massive user of power. And if you imagine, the gas prices that we had then are nowhere near the gas prices that we have today. And with we had a deal that was with Enron in terms of our gas price, which was a very, very good deal. Enron went where Enron went, and then gas prices just elevated to the point where it became very, very uneconomic to do any more drying. The Howden Sludge Treatment Centre that I mentioned before, we had an existing dewatering and liming plant there, which rotted, and we ended up working with Agravert and came up with an innovative solution, which was one centrifuge and processing all of the sludge at Howden. So that was up to 35,000 dry tonnes through one centrifuge, and then lime stabilising it and send it out to agricultural land. Now, lime stabilisation was a bit of an issue for us in terms of our customer base. It got us away as far as our processes were concerned. We could keep on treating sewage, and we found we had an outlet for it, but we had massive customer issues right across Northumberland during the spreading periods. At one point, because I have to declare I am a farmer as well, and I did take the lime stabilised product onto our land, and my wife threatened me that if it came on again, she was off. So I did a bit of a cost-benefit analysis and decided it was cheaper to stop taking the lime stabilised sludge. So 2006 came around, and there's a bit of a story around this as well. Because I was looking at different things for different reasons. I went to IFAT in Germany, and I stumbled across the Canby stand at the IFAT works. And I was with Alexander Madden at the time from Agravert, and I didn't have any particular interest because we were kind of world champions as far as sludge drying was concerned. And we were never going to change away from that. That was before we knew about the gas prices. But Canby were quite persistent, and they put this guy onto me, which was a guy called Keith Panter. And Keith Panter was very persistent. And in the end of the day, I pushed Mike Rucastle, who was our sludge strategy manager at the time, onto Keith, and kind of suggested to him, go out and have a look, see what you can give us, that sort of thing. It got rid of him. But anyway, I sent him to 3 plants to have a look at. And we were just reminiscing about this morning, which was our Sunderland plant, Hendon, our Teesside plant, Brands Hatch, and our Newcastle plant at Howden. And Keith and Mike went away for a day, and he actually produced the quickest feasibility study that we've ever known within Northumbrian water. It took him 2 weeks, and he came back with an answer for me around what things could change as far as the overall sludge strategy was concerned. And he actually convinced me at the time, instead of looking at those 3 plants, go down to 2. And then we talked through what we could do from a sludge transportation point of view. And the answer that we came back with was actually a bit too good to be true. The numbers were quite astonishing in terms of what sort of a transformational change we could go through to actually do that. And in fact, in reality, they were even better than that when we managed to get everything on the ground. So things that were really causing us some big issues, and this is why the cost differential made a big difference to us, is that we just couldn't maintain these dryers. We couldn't keep them running. They were wearing out. They were costing a lot of money for us to maintain. And the other element to it as well, and this is kind of This is something that's got even more and more of a positive note for us as we've progressed with our overall strategy story, is that there was an opportunity there to be a bit more green than we were, or certainly a lot more green than we were when we were using all that gas to do the drying. So we came up with a strategy which was all around building 2 advanced anaerobic digestion plants at locations at Brands Hatch and Howden. We did a lot of work with Aqua in terms of doing the testing around our sludges to see whether we could do exactly what Keith was suggesting to me we could do in terms of that conversion rate. There was some strange elements to Brands Hatch, because Brands Hatch is 3 sewage treatment works in one and takes a lot of industrial imports into it, so we needed to know whether it was going to be suitable to do the overall process there. At a late stage, Keith tried to introduce enzymic to us. Unfortunately, the project manager I had at the time, we managed to steer him away from that one altogether. So we didn't listen to him all the time. But anyway, there was some significant costs to be made to overcome. But this gave us the opportunity to deal with all of our sludge that we had in the region. It gave us energy from waste. It gave us reduced CO2 footprints, gave us that great odor potential reduction, and we could do something. We would have a product which was safe and reliable for our recycling operations going forward. The transport element that I mentioned before was really just making sure that we didn't tanker as much as we were doing, and we could squeeze the water out of it at strategic locations and then bring that in as a cake to those 2 advanced plants. So just showing that on a bit of a map there, the red spots that you see on there are our dewatering centres. So they are purely sewage treatment works that can actually take the effluent stream from the centrifuges and be able to load everything up onto a truck and carry that forward to either of the 2 AAD locations. And they give you some figures there in terms of what we were dealing with and how we could make the change around the overall transport strategy. So the other element to it that helped us with the decision making was around the renewable obligation certificates that existed at the time. And also the fact that we had 2 power sinks at both Howden and Brand Sands where we could utilise the electricity that we could produce from the combined heat and power engines that we would have there. For the likes of Howden, we could actually supply the whole of the electricity for the Howden plant and 50% for the Brand Sands plant. And that gives you a bit of an idea in terms of just how green we could turn ourselves over that period of time. So I wish I could do that all over again and get ourselves down to the net zero point. But it's something that we've bagged over time, and we continue to do so. So I'm not going to take you through the process as such, because Tony will do that in his virtual tour. But that's a bit of a picture in terms of what we installed at Brand Sands. So you see there, we've got 3 digesters. We replicate that at Howden. We've got combined heat and power there. We've got the THP plant, the Canby process that we chose, and the cake reception. Now, we managed to build that in 2009, and that had an immediate change in terms of our overall finances. We were treating sludge from a drying cost point of view, something round about the £650 a dry tonne. And just by the flick of the switch overnight, when we commissioned that plant there, we turned that into minus £40 a tonne. So it was a massive transformation for Northumbrian Water. I wanted to build both plants at the same time, but at the time we just didn't have enough cash to do that. It was a difficult enough job to convince our board at the time to move to AD from the World Championship position that we were in. My previous boss had likened it to talking to the Man United board and telling them that they should start playing rugby. But they took it just the same. And I'm not going to go through the process because Tony's going to do that. That gives a different type of overview, although it's not the as-built. But those 2 blue buildings that you see there, they housed our 7 drying plants there. And then we squeezed AD into the bottom right-hand corner of the process there. And my only regret is it's got 4 digesters there. I wish I had 4 digesters. I've only got 3. Howden, we did something very, very similar. And that gives you a bit of an overview of what Howden there. You'll see more of that in the video. Howden's a much more compact site, but the development that we went through between the design of the Brand Sands plant and the design of the Howden plant was quite significant. We're probably about 10% more efficient in terms of what we managed to achieve at the Howden plant compared with the Brown Sands plant. And that just gives you some more views in terms of sludge cooling, but just a bit of a reference there in terms of that. We've still got a lot of heat to get rid of as part of our AAD process, and finding a home for that would be something that we would really desire to do. And again, we've been talking a bit about that already today. So, and I put 2 photographs up there. I asked Tony to give me a photograph the other morning in terms of our gas bags, because we started off with those 2 gas bags there as gas collection items there. Now, they were there really as just as pressure regulators, but as things moved on and as we progressed with our strategy a little bit further and got into gas to grid, we just didn't have enough gas capacity in there for the customer that kept rejecting us. So we needed to increase there. So it looks like there's a bit of an oversized gas bag in there, which is what Tony got us. So the other elements to our strategy were all around making sure that we could recover as much heat as we possibly could. We have effectively 3 engines that are attached to AAD at Howden and 3 engines attached to the AAD at Brown Sands. We actually installed an extra engine at Howden just to be able to generate even more energy because of the gas we were producing. We've also done other efficiency types exercises in terms of wrapping up all of those pipes, trying to retain as much heat as we possibly could so we could then recover it as part of the Canby process there as we fed the sludge in. So we were always feeding warm sludge into the Canby process. So we've made some pretty good efficiencies just even after the construction of these plants. So we take ourselves a little bit further forward, and whilst we enjoyed reasonable money that came from the renewable obligation certificates at Brown Sands, Howden, because it was a little bit later, only got half a rock out of that. So the business case became a bit more interesting when RHI came along, and we decided to pursue the route of injecting our biomethane into the grid. The only difficulty is we had to scrub it, we had to clean it all up, and we also have to add propane in this part of the world because we can't match the CV that comes in from the North Sea. Other areas in the country don't necessarily have to do that, but it added an extra bit of complication to the whole thing. But we managed to do it, and in 2014, Tony describes these as his Christmas presents. I gave him another Christmas present in December 2014, and we ended up with a gas upgrade plant, which was, again, a massive game changer in our overall finances as far as the company was concerned. Now, I'm not going to take you through the process there, but because we still had CHP engines, and there still was a lot of life as far as the CHP engines were concerned, and we still had a power sink as far as the sewage treatment works were concerned, we chose to use the combined heat and powers because we wanted the heat back over again. So we not only produce the green gas and push it into the grid as a renewable gas there, we then buy it back out of the grid as natural gas to run the CHP, because the margin between what we can produce from a CHP electricity that we can use and what we can buy from the grid is great enough to do that, and we'll continue to do that. And at the moment, the way that things are moving price-wise, the gap is widening again, so it looks like we'll be doing that for quite some time yet. So we'd done it at Howden, so we decided to do it again at Brown Sands. So in 2020, that was the final part of our strategy as it currently stands to install that extra gas to grid plant there. doesn't have the same sort of tariffs as the Howden RHI has, but again, it still works for us financially, and we do the similar sort of thing as you saw in that process diagram I had before there at the Brown Sands plant. So there's been a few lessons as we've gone along the way as part of the strategy there. And one of the most important things, and again, we struggle to get this across sometimes to the likes of Ofwat, that there is such an independency between the sewage treatment works that you need to manage and the AAD plant that you've got sitting on top of it. Dealing with those liquors is equally as important as dealing with the sludge that's arriving from the plant there. And that's why I still have my managers looking after both the AAD plant and the sewage treatment works. And to me, it should never change from that. Mr. Llewellyn here, he creates tensions in terms of what we need to push through the plants, that sort of thing there. But he does work for us. So we do strike a great balance around that, and we are pretty efficient in terms of doing it. And we are deemed the sort of frontier as far as the overall sludge strategy is concerned in the UK. Dewatering, the massive learning I got from the Agravert arrangement that we had at Howden was that a centrifuge can do a hell of a lot more than the belt presses that we were relying on were actually achieving. At Brown Sands, there were 7 drying lines, but there was 14 belt presses. Now, the thing that I never understood until we stripped it all back and tried to use the belt presses for our dewatering process at Brown Sands was how unreliable they were. We always blamed it on the dryers, but the belt presses were absolutely hopeless. So we actually did a retrofit also at Brown Sands and put centrifuges directly in front of the Canby. Struvite and grit management, we've heard a bit about how we might deal with that this afternoon in this room here. We've still got a lot of work to be doing on that. We've put in extra pipelines just to try and deal with that. The only other thing that we've been doing is trying to empty digesters, and we haven't necessarily managed to empty the digesters at Howden, but we've already done it once at Brown Sands. We need to do it all over again. We need to maximise on our heat recovery, as I mentioned before, and we've had efficiency schemes where we've actually delivered all of that there. Getting gas into the grid is a difficult job, and managing the specification of the gas that has to go through the chromatographs and into the grid, it's a nightmare at times. Just on instrumentation, on the odorant kit, that sort of thing there. We learned huge lessons as we went along, just getting our skills up to speed with what our most discerning customer in Northumbrian Water would come up with. Tony has a one-to-one relationship with NJN, talking to them, asking them why they chucked them out again. But we are probably the most reliable plant that is actually putting into the grid at the moment, regardless of what process is upstream of it. Automation and skilled operation, you can automate a lot, but at the end of the day, some bits you can't. In terms of the gas to grid element to it, it does need a lot of babysitting. I was sold a bit of a pup in terms of the automation element to it. I ended up having to employ more people just to sit and babysit that there. And what amazes me is just how skilled and how knowledgeable the guys are when they're actually running these plants. And we had a few single points of failure as part of our design, and when we went through things, we contemplated just how things would fail, how we would get extra conveyors in to move sludge around when you lost that centrifuge and you had to bring a temporary centrifuge in, that sort of thing there. So there's quite a bit of thought done up front around that, and a bit of adaptation. And the other bit is planning and managing our shutdowns. That is a huge job for us. And it's done quite successfully and quite swiftly. The thing that we haven't done a great deal of, which is the emptying of the digesters, does take 3 months to actually do one digester. But the management around the likes of the thermal hydrolysis process, we've got them down to two-week windows now, and they are well, it is like watching a clock work when our guys do it. So a lot of praise around them. I do have a wish list as far as our strategy is concerned. I nowhere near have enough raw sludge capacity. The ships actually used to help us do that, but we did offload the ships. And also digestion capacity. I could do with an extra digester at both of these locations here. And there's probably a business case around just the downtime associated with it and the lost revenues associated with just doing that. And the other thing that he always is moaning about is cake storage. I never have enough cake storage where we can drop stuff on the concrete for bad weather, for other things that happen to us. We could do with a hell of a lot more of that. And I'd love to also find a use for the low-grade heat. And I've had some ideas today just from talking through to a few individuals around there. Just finally from me, just a bit of acknowledgement. Keith's been here 20 years, so I'm told, every year. And yeah, you try and duck and make sure he doesn't see you, but no, he's a good guy. He made a massive difference for us as far as our overall strategy was concerned. Donna, who's probably watching online now, she was here earlier, who actually helped me build the overall plants that we've got. She built both plants. She's trying to extend Howden for me as it stands at the moment. And also Alexander Madden, who helped me through some pretty difficult times with some innovative ideas, and certainly the knowledge that he gave us around just how you could manage dewatering operations. And then finally, my team. Whilst it's a lot easier than trying to dry sludge, the AAD process is heavily maintenance and operation dependent. And I do think our guys have developed a huge amount of knowledge in terms of how to do things, when to do things, and that has been paramount in terms of the success of our overall operation. And then I had to mention them. My Bioresources team, some of which are here, and Alec looks after that team there. And the only thing that he really got out of it was a change in job title. I used to call him my shit manager. He's now my Bioresources manager, but he's still shit. But anyway, that's all I wanted to cover.
Cheers. Right, thanks very much, Richard. That was the background. We've now got a video with Tony will be narrating all the way through. So that's fantastic. We'll watch that video and then we'll do a Q&A session after that. Thank you.
Hi, I'm Tony and welcome to Howden Sewage Treatment Works, where I'm going to talk you through how we treat the sewage and also how we treat wastewater sludge. Here we are inside the primary treatment area, where after the raw sewage has been screened and degritted to remove any large particles, the sewage then enters the primary treatment area where we settle the layers of sludge, the raw solids to the bottom of the tank, where the top layer carries on throughout the process to the next area of treatment. Following the primary treatment of the raw sewage, the top layer, which is still a bit too dirty to go into the river, comes up here to the activated sludge plant, where our special bugs actually eat the sewage and clean it up prior to it going into our final settlement tanks behind. This is the final stage of our activated sludge process, where the treated effluent overflows from our final settlement tanks and enters safely into the river. Following the processes on the sewage treatment works, where we take the liquid sludge from the bottom layer of the effluent, that is then sent to the dewatering facility behind, where we spin the sludge at high speeds to drive off and squeeze out as much of the water as possible to leave a soil-like textured cake product. These are the boilers which produce the steam to cook our sludge in our pressurized sludge process. The dewatered sludge from the previous process is then sent here, where it's cooked at high temperatures, similar to a pressure cooker at home. But here it actually kills off any of the harmful bugs and bacteria left in the sludge. The cooked sludge is then depressurized which actually causes the sludge cells to explode before they move on to the next stage of the process. In the digesters, our bugs actually eat the broken down sludge. Whilst doing this, they burp and pump and produce the biogas, which we use to run our engines on. The biogas produced in our digesters is then stored here in the biogas holders before it's then sent to the engines. The engines take the biogas produced by the digestion process and convert it into energy, which we use to power the rest of the sewage treatment works. Once the digesters have finished their job, the remaining sludge can then be dewatered to produce a nutrient-rich, bug-free biosolid, which can be used in agriculture as a fertiliser.
So great. I think great presentation. So I'm going to open the floor for some questions. So thanks, Richard and Alec, and hopefully we've got plenty of questions for you to answer. Come on. Another one over here.
Yeah, just curious why I went for the PSA, biogas upgrading, pressure swing absorption, rather than any of the other options.
Tony, do you want to do that? Yeah.
So the idea behind the design of the gas degrade for it's a water wash system. So we're a water company. So when Richard sent me across to as a part of a team across to Sweden to have a look at the different types of technology, I think some of my background with the wastewater treatment process and looking at odour control and the odour control scrubbers, and we have 15 of these at Howden, and it just looked very similar to that type of system. So that was the idea behind that, really, was just we're a water company, it was a water absorption system, and it looked really familiar to me, which was a bonus. Okay.
There was very little price difference between the two, and yeah, there's the methane slippage element to it, but he wanted to use one of them.
I think we have another question over here.
Thanks, Amanda Lake from Jacobs. Thanks, that was really interesting. I just wondered how climate resilient, or what are the risks around your current strategy in terms of, I guess, exporting biomethane, importing fossil gas, and what could shift that? Whether a carbon tax, or what are the kind of sensitivities, and what might keep you up awake at night in the future, maybe?
We're probably there at the moment. Land and recycling to land is probably our biggest issue. We can generally overcome most of the other things to it, and we're just asking for some proper logical thought process, as we were talking before on the previous presentation, in terms of how you apply that level of regulation to that there. It's such a vital it's such a precious resource as far as the nutrients are concerned that it would be criminal to do anything different with it. But we've maybe got to get better in terms of how we process that to make it acceptable for a continuation of that recycling activity. As far as other things are concerned, yeah, the overall pricing of gas and stuff like that is we're pretty okay with, but one of the things I do want to do is try and get rid of our dependency on our sacrificial elements to using gas as well. So if we can remove those bits, that gets us that extra bit of efficiency again. alternatives to the recycling is something else that we're looking at in terms of what else could you do with it? Where else could they go? What else could we use it for? So we're not stopping looking in terms of all of our strategies around that. So all of the elements of risk we haven't got the answers for, but we're certainly thinking about them at the moment, because we can't just sit still.
Thanks very much.
Any other questions? Way in the back.
Thanks. Mark Christensen and Religion. Being a son of a farmer, and yourself, Richard, you mentioned you were a farmer. Have you looked at the comparators in terms of your land bank challenges on the comparator side of end of waste, where you're essentially producing quite a high quality pathogen-free cake compared to raw manure and slurries, which full of pathogens and nutrients, often a lot of diffuse pollution issues around storage for months on end, and also the artificial input in terms of that sort of working with the agronomists side of your end customers, and the artificial impact of CO2 being a pollutant now, which is obviously recognised last week quite significantly.
Yeah, I mean, we see our product as being a pretty reliable slow release product, and what concerns me and what grumbles me, and Alex heard me grumble about this over and over again, that we keep trying to classify one product as being the root to all evil as far as the agency is concerned, whereas different things, the likes of digestates and our products, give off different forms of leachate, and it doesn't matter. You've also got to compare the soils that you're applying it to as well. We see this as being a valuable resource. It's got all of the P that you could possibly want as far as wheat production is concerned, and it gives you a good starter as far as nitrogen is concerned in the spring. It's in the right place at the right time to do that, and the level of leaching from there, we are arguing from a scientific point of view with the agency on that. I think it's it's not the be all and end all. It has to complement your nutrient input to any crop delivery. Malik?
Yeah, sort of building on what Richard said in the question, is that we haven't talked about it today, but Biosolids has the Biosolids assurance scheme as well, which we can build on. We can use that, and we haven't talked about what David did. It's about stakeholder engagement as well. So we need to actually make sure our stakeholders, farmers in this case, and then British Retail Consortium was talked about earlier on, we can actually build on that as well, because as Richard said, there's only one land bank, and we've got to make sure that we can actually go to it in a holistic way. And that's part of the problem which may be talked about tomorrow in the open forum, is that we're not looking at biosolids holistically. We're trying to look at, or our regulators are looking at one thing. We should actually look at the package, and can be, so we've got an enhanced biosolid. It's a fantastic product. Stakeholders want it. Most of the water companies sell it. We're the only one who puts it through total THP, and we get gas to grid for it. So I would back up my boss and my colleague that we're leading. But we can't rest on our laurels. We've got to make sure that we're engaging our stakeholders and taking it forward, because it is difficult. So.
Thank you. Time for a final question. Oh, I see two. Okay. Two more.
Charlotte Monkhouse from Macroenviro. It wasn't mentioned in the video, but I'm guessing you do screen the feed that goes to the digesters. Have you ever considered putting in a better kind of screen to give more assurance on the biosolids that come out on the back end?
We do screen. So we screen at the front end of the sewage treatment works, and we screen the sludge as it goes through the process. As far as finding an alternative screen that can handle the volumes that we're talking about, we're always on the lookout. I think that's a good point in terms of anybody that's out there that could develop us one to do that, because microplastics is an issue as far as the overall recycling agenda is concerned as well.
Final question, way in the back.
I know, he called us.
Hi, Rick Lancaster from Atkins.
you've very proudly boasted to being number one in the industry on unit rate. How confident are you you're going to be able to maintain that? And why?
What sort of a question is that, Rick?
nice, easy one to finish with.
We are some way ahead in terms of the overall sludge strategy is concerned. We are not sitting on our laurels. We are looking actively at all of our processes, existing and otherwise, with a view of trying to maintain that position, trying to maintain our energy efficiency out of that. So I don't know how confident we can be, because others, I mean, everybody wants to copy. You did when you were there. I can remember presenting the stuff to you guys some time ago when you were still thinking about incineration. So
yeah, and we were getting pestered by Panther just as much as you were.
Yeah. So I mean, I used to do world tours. It used to be a joke. I used to have a T-shirt with all of the touring I used to do. We need to do a bit more of that. See what's out there. Pick up on everything that's around this type of conference. I've learned stuff today that I want to try out. So that's how I'm going to try and maintain it, Rick.
Thank you.
All right, I'm going to finish up for the rest of the day. I think it was an interesting day. A lot of good presentations, good questions. Tomorrow we have the forum, of course. So I hope to see you guys all tomorrow. And if not, you can try your luck on Saturday, because Newcastle's playing here.
Yeah.
And I have a feeling they're going to win for the first time this season.
So have I. Yeah. and I just hope our new owners managed to achieve the same transformation that we did with sludge.
Absolutely.
There you go.
Okay. Thank you all, and have a good evening. Thank you.